Hello, and welcome to the sleepy universe. Among the countless worlds orbiting distant stars, there is a concept often spoken of by a very beautiful name, the habitable zone. That name makes it easy to imagine a gentle region of space around a star, where a planet is not too hot, not too cold, where water can remain on the surface, and where life might begin a very long story. But if we look more closely, the habitable zone is not only a matter of distance. A planet can stand in the right place and still fail to keep its water. It can receive the right amount of light and still have its atmosphere turn it into a harsh world. It can once have had rivers and lakes and then lose its sky to space. To understand why a planet can truly become temperate, we need to go deeper into things more silent than distance. Atmosphere, pressure, clouds, water, rock, the parent star, and time, so long it reaches beyond every familiar measure of human life. A star can shine for billions of years, so steadily that from a great distance, its light seems like a stable breath in the darkness. Around that star, dust and stone once gathered into planets, each world carrying its own orbit, its own mass, its own sky, if it was fortunate enough to hold on to an atmosphere. Among those orbits, there is a special region often described as the place that is neither too hot nor too cold, where energy from the star may be just enough for water not to be forced into permanent ice and not to be forced to evaporate away from the surface. Seen from far away, the idea is beautiful. A planet stands at just the right distance, receiving light gentler than fire and warmer than ice, and from that, the possibility opens for oceans, clouds, rain, and quiet chemical reactions stretching across time. But the beauty of that concept can also make it easy to misunderstand, because a planet standing in the right place around a star is not necessarily a gentle world. The right distance is only like placing a vessel in a suitable region of light. Whether that vessel holds water, trapped heat, air so thin it can protect almost nothing, or pressure so heavy that the surface becomes unfamiliar, is another story entirely. Starlight does not determine a planet's climate through one simple straight line. Before that energy reaches the ground, the light has to pass through the layer of gas surrounding the planet, if such a layer still exists. Some of the light may be reflected by clouds back into space. Some may be absorbed by oceans, ice, deserts, or rock. Heat from the surface does not simply disappear immediately, but can be held within the atmosphere by water vapor, carbon dioxide, methane, and many other gases. Winds can carry heat from the bright side to the dark side. Oceans can absorb energy into deep layers of water and release it slowly. Ice can expand, reflect more light, and make the planet even colder. Clouds can both cool what lies below and hold warmth above. With only a change in atmospheric thickness, gas composition, surface pressure, rotation speed, or the amount of water, a planet can follow a completely different fate, even if its distance from the star still seems to place it within a promising zone. Within our own solar system, the three rocky planets closest to this story show that distance is never the only answer. Venus, Earth, and Mars all orbit the same Sunday. All were born from the material of a young planetary system. All are rocky worlds rather than giant balls of gas. If we looked only through the imagination of an age before spacecraft, people might once have thought of Venus as Earth's warm, humid sister, and Mars as a colder, drier land that still carried a few familiar features. The deeper reality is far more severe. Venus is close to Earth in size, but its dense atmosphere traps heat intensely, making the surface a harsh place beneath a heavy layer of carbon dioxide. Mars went in the opposite direction. Its landforms show that water once flowed there, carving channels, leaving behind ancient riverbeds and sedimentary regions. But the present atmosphere is too thin, the pressure too low, and the surface too cold and dry for liquid water to remain for long as it does on Earth. Between those two extremes, Earth has held on to something rarer than the familiar beauty of a blue sky. an active balance among atmosphere, oceans, clouds, rock, light, heat, and time. If someone asks only how far a planet is from its star, the answer is like knowing the address of a house without ever stepping inside. That address may tell us what kind of climate region the house is in, how much sunlight it receives, whether it is near the sea or near a desert, but it does not tell us whether the walls still stand, whether the roof can keep out the rain, whether the windows open, or whether the inside holds breathable air, or only a cold, empty space. A planet is much the same. Distance tells us the average amount of energy a world receives, but not how that energy is handled. A surface covered in white ice will reflect light differently from a dark ocean. An atmosphere rich in water vapor will trap heat differently from a thin atmosphere with almost no power to shelter the surface. A slowly rotating planet may have long days, long nights, a bright side that is scorched, and a dark side that falls into deep cold. A faster rotating planet may distribute heat through complex bands of wind and ocean currents. With the same number for distance, the universe can create so many kinds of surfaces that we cannot quickly call a world habitable simply because its orbit appears to be just right. Water is usually placed at the center of every thought about habitability, because on Earth, every known living thing needs water in one way or another. But liquid water is not only the result of pleasant temperatures. A drop of water on a planet's surface needs a stable enough context in which to exist. If the pressure is too low, water can evaporate or change state too quickly, without enough time to form lasting lakes, rivers, or seas. If heat is trapped too strongly, oceans can be pushed into a stage of thick water vapor, strengthening the heat-trapping effect and causing the planet to slide away from a temperate state. If the atmosphere gradually escapes into space, surface water loses its support as well, while the traces of ancient flows remain only as memories carved into stone. Seen with a more careful eye, the habitable zone is not a place where water is guaranteed to flow. It is only a place where water has a chance to exist, if the other conditions also help support that chance. Even more importantly, water does not only need to be present, it needs to participate in the climate life of the planet. On Earth, the ocean does not sit still like a vast blue mirror. Water evaporates under sunlight, rises into the atmosphere, gathers into clouds, falls as rain or snow, moves through mountains, plains, and rivers, seeps into soil and rock, and then returns to the sea in cycles that never stop. Every step in water's movement matters. Clouds change the way the planet reflects light. Water vapor holds heat and creates weather. Rain wears down rock, drawing some carbon out of the atmosphere through slow geological processes. Rivers carry material from continents to the ocean. Ice preserves memories of climate in cold layers stacked through time. Through these movements, water is no longer just a liquid lying on the surface, but becomes a thread connecting sky to stone, connecting the weather of individual days to climate stretching across millions of years. A planet that stands inside the habitable zone but lacks a stable water cycle may only be an unfinished promise. Water may be locked beneath ice, buried deep underground, held as vapor high in the atmosphere, or appear only for brief moments before vanishing. Life, if understood through the experience of Earth, does not need only a single wet moment. Complex chemical reactions need an environment that can repeat, nourish, and endure for a long time. A temporary pond after a meteorite impact is very different from an ocean that lasts for billions of years. A layer of ice hiding deep water beneath it is different from lakes and seas that exchange directly with the atmosphere. A planet with a few signs of water in the past is different from a world where water is still moving through clouds, rain, rivers, oceans, and rock. Distance from a star can create a suitable average temperature, but the durability of water is what makes habitability far more meaningful. The most familiar way to imagine it is as a belt around a star. Inside that belt, the star's warmth seems just right for liquid water. Closer to the star, a planet may receive too much energy, causing water to evaporate intensely, water vapor to rise in the atmosphere, the heat-trapping effect to grow more powerful, and the surface to gradually slip away from a temperate state. Farther out, the energy received declines, ice can expand, the surface reflects more light, the climate becomes deeply cold, and surface water, if present, is more easily locked away as ice. But even that image of a belt is only a simplified diagram. The inner edge and outer edge are not hard lines like borders on a map. They are transition regions that depend on atmosphere, clouds, pressure, gas composition, rotation speed, the amount of water, geological activity, and the nature of the parent star itself. A world near the inner edge may still avoid being heated to an extreme if its clouds reflect enough light. A world near the outer edge may still hold on to warmth if its atmosphere is thick enough and rich enough in heat-trapping gases. Distance begins the calculation, but it does not close the fate of a planet. What makes this concept useful is its power to filter. When telescopes find thousands of planets orbiting distant stars, humans cannot observe all of them with the same level of attention. Some planets are too close to their parent stars, moving quickly through hot orbits with surfaces that are likely scorched or atmospheres that have been strongly altered. Some planets are too far away, receiving so little light that surface water, if present, would be difficult to maintain in liquid form without special conditions. The habitable zone helps select more promising targets, places where the amount of energy from the star has not ruled out the possibility of liquid water from the very first step. In a sky filled with faint data, this is how human beings set priorities. Not because life has already been found, but because a position has been found where questions about water, atmosphere, and surface become more worth asking. Each star has its own habitable zone. Around a star brighter and hotter than the sun, that zone lies farther out because a planet needs to stand at a greater distance to avoid receiving too much energy. Around a smaller, dimmer, cooler star, the zone moves inward because a planet has to orbit closer to the parent star to receive enough light for its surface not to freeze completely. This idea makes planetary systems across the universe more diverse than ordinary human intuition might suggest. Not every world capable of holding water has to orbit a sun-like star at an Earth-like distance. A planet around a red dwarf may lie very close to its parent star and still receive only an amount of energy comparable to that of a more distant planet around a brighter star. A planet around a larger star may need to stand much farther away to have any chance of keeping a temperate surface. So the habitable zone is not a fixed distance in space. It is a relationship between a planet and its star. But the diversity of stars is exactly what makes the story more complicated. A star is not only a lamp shining on its planets. The parent star also emits ultraviolet light, X-rays, stellar wind, and bursts of energy that can affect the atmospheres of nearby worlds. Around small, dim stars, the habitable zone is often very close to the star, so a planet may receive enough light while also facing a stronger space environment, especially if the star is young and intensely active. A planet in the right thermal zone may still gradually lose its atmosphere if radiation and streams of particles from the parent star erode the surrounding layer of gas for too long. A world may begin with water, but if high-energy light breaks apart water vapor in the atmosphere and hydrogen escapes into space, that water supply can diminish over time. In this sense, the habitable zone does not only ask how much visible light a planet receives. It also has to consider the full temperament of the star that is both nourishing and testing that planet. Another common misunderstanding lies in the word habitable. In everyday life, when people say a place is livable, they often imagine breathable air, pleasant temperatures, safe ground, drinkable water, moderate light, and even some feeling of familiarity. But in astronomy, when a planet is called potentially habitable in the basic sense, the standard is usually far more modest. The initial focus is the ability to maintain liquid water on the surface, because liquid water is the solvent of life on Earth and the most convenient sign with which to begin the search. That does not mean the atmosphere has to be exactly like Earth's, or that the pressure has to match Earth's, or that the sky has to be blue, or that the oceans have to be salty in a familiar way. This concept is not searching for a complete copy of home. It is looking for places that may preserve one important foundational condition: liquid water stable enough for complex chemical processes to have a chance to unfold. Even liquid water on the surface is not easy to confirm on a distant planet. On Earth, humans can see the oceans, measure rainfall, track clouds, sample water, observe rivers, and gradually understand how the climate operates. For exoplanets, most of those things lie beyond direct view. Scientists may know that a planet passes in front of its parent star, dimming the starlight by a very small amount. They may estimate size from the amount of light blocked, estimate mass from gravitational effects, and infer density to guess whether the planet may be rocky, gaseous, or something in between. With some luck, starlight passing through the planet's atmosphere may carry the signatures of certain molecules. But from a signal like that to the conclusion that liquid water exists on the ground is still a long journey. Water vapor in an atmosphere does not necessarily mean there is a surface ocean. A planet close to Earth in size does not necessarily have Earth-like pressure. A beautiful orbit does not necessarily mean there is rain, rivers, a water cycle, or a long enough period of stability. For this reason, the habitable zone should be understood as the first layer in a multi-layered filter. The first layer asks about energy from the star. The next layer asks about the planet's size and mass. A planet that is too small may have difficulty keeping an atmosphere over long spans of time. A planet that is too large may hold a thick layer of gas, or become a world without a clear rocky surface in the way Earth has one. The next layer asks about the atmosphere, whether it remains or has been lost, whether it is thick or thin, which gases it is rich in, how strongly it traps heat, and how it reflects light. Then comes surface pressure, which determines whether water can remain in liquid form. After that comes water itself, not only as a molecular sign, but in terms of location, amount, state, and the ability to circulate through the atmosphere, surface, and rock. Finally comes time, because a world that warms for only a brief period and then loses its atmosphere, or has water only briefly after impact events, is very different from a planet that maintains relatively stable conditions for hundreds of millions or billions of years. The concept of the habitable zone also has an important limit. It focuses on liquid water at the surface. This is very reasonable when searching for Earth-like worlds, because the surface is where starlight, atmosphere, water, and rock can meet directly. But the universe holds other possibilities as well. In the solar system, there are icy moons far from the sun that still draw attention, because they may have oceans beneath their ice, kept warm by gravitational tides and internal heat. Those places are not in the habitable zone in the classical sense around the sun, because their surfaces are too cold for liquid water to lie exposed beneath the light. Even so, hidden oceans may still be chemically interesting environments. This does not make the concept of the habitable zone useless. It only reminds us that it is a tool with a clear scope. That tool is especially powerful when searching for planets with liquid water on the surface, but it cannot contain every kind of environment that might nourish complex chemistry in the universe. One more subtle point is that the habitable zone is not the same for every kind of life. If we are speaking of simple microorganisms, the necessary conditions may be very different from those required by complex life, which needs more energy, a stable environment, suitable gas concentrations, and stricter chemical limits. Earth had microbial life for a very long time before there were large animals, forests, or complex ecosystems. A planet may be good enough for simple biological chemistry, but not necessarily stable enough, rich enough in oxygen, gentle enough in climate, or safe enough from radiation for complex life. That is why, when we hear the word habitable, we need to keep many layers of meaning in mind. Habitable for liquid water is one thing. Habitable for microorganisms is another. Habitable for complex organisms is a much higher threshold. Careful science does not blend those layers together because each layer requires different evidence. The image of a Goldilocks zone is often used to make the concept feel more familiar. Not too hot, not too cold, just right, as in a familiar fairy tale. That image is useful because it helps listeners immediately sense the role of thermal balance. But if we keep only the image of just right, we can easily forget that a planet is not a bowl of porridge cooling or warming in a kitchen. A planet is a dynamic system with a moving atmosphere, circulating oceans, ice that expands or retreats, volcanoes that release gases, rock worn down by rain, a magnetic field that may shield against part of the stellar wind, an orbit that can change over time, and a tilted axis that can create seasons. The true Goldilocks zone is not a fixed, peaceful circle. It is a place where all of those processes have a chance to work together well enough for liquid water not only to appear, but to remain and take part in the planet's history. From far away, Earth is also only a planet inside the Sun's habitable zone. If another civilization observed the solar system from many light years away, they might see Earth crossing in front of the Sun as a tiny shadow, measure its size and orbital period, and perhaps detect traces of an atmosphere containing water vapor, carbon dioxide, ozone, or other signals. But even with those signs, understanding what Earth truly is would still require many layers of evidence. They would not immediately see the Amazon rainforest, hear the sound of ocean waves, know exactly which mountain range rain was falling on, or which polar ice was cracking apart. That helps us become more humble when we look at other planets. If Earth itself sends only such small signals from far away, then distant worlds cannot be turned into certain stories from only a few initial pieces of data. In the end, the habitable zone is a way for human beings to ask better questions before the vast darkness. Instead of vaguely asking where life might exist, we begin with a more specific question. Where could liquid water remain on the surface? From that question, we move on to atmosphere, pressure, clouds, seas, rock, radiation, the parent star, and time. Each layer makes the story more complex, but also more real. That very complexity is what makes exoplanets so compelling. A planet does not need to be declared alive in order to matter. The fact that it stands where starlight may allow liquid water, while the remaining conditions are still unknown, is already enough to turn that world into a small point worth following in space. Because sometimes, in science, the value of a concept does not lie in giving us the final answer, but in showing us where to listen to the universe first. Distance from the star is still the first thing that must be taken seriously. Because before there is atmosphere, cloud, ocean, or any cycle on the surface, a planet has to receive energy from the place that lights its entire planetary system. A star is not only a bright point hanging at the center of an orbit, it is the main source of heat, the main source of light, the energy clock that every surface, every layer of gas, every crystal of ice, and every drop of water must answer to. When a planet orbits closer to its star, more light pours down onto it. When its orbit carries it farther away, the same surface receives less energy. That change does not rise or fall gently in the way ordinary intuition might suggest. If the distance doubles, the amount of light on each unit of area falls to only 1/4. Even a small change in orbit can create a large difference in the heat balance of a world, especially when the surface is already near the boundary between liquid water, ice, and water vapor. The way a planet receives light can be seen as the first step in its climate budget. Each day, energy comes in from the star. Part of it is reflected back into space by clouds, ice, atmospheric dust, or bright-colored surfaces. The rest is absorbed by rock, oceans, the atmosphere, and darker ice. The surface then radiates heat back out, But that heat does not always escape easily. Heat-trapping gases can hold on to part of the energy, making the atmosphere and the ground warmer than they would be if the planet were bare and had no surrounding layer of gas. So distance is not a number that stands alone. Distance determines the amount of energy coming in, while the atmosphere and surface determine how that energy is reflected, absorbed, retained, or released into space. A world may begin with the same level of light, but if its cloud layer is thicker, its surface brighter, its oceans wider, or its heat-trapping gases more abundant, its final climate can turn in very different directions. The star-facing inner edge of the habitable zone is where the problem becomes sensitive. When a planet receives too much energy, surface water evaporates more easily. Water vapor is not only a sign of warm seas or frequent rain. Water vapor is also a powerful heat-trapping gas. If the atmosphere contains more and more water vapor, heat from the surface has a harder time escaping, causing temperatures to keep rising and making even more water evaporate. That feedback loop can push a planet in a dangerous direction. The hotter it becomes, the more water vapor there is. The more water vapor there is, the more heat is trapped. The more heat is trapped, the harder it becomes for oceans to remain. In planetary climate models, the inner edge is often linked to limits such as water loss or a greenhouse effect, moving beyond the familiar balance state. Once that limit is crossed, a planet does not merely become a few degrees warmer. Its water and atmospheric systems may shift into another state, one where the surface gradually loses the ability to maintain stable oceans. It is important to note that a planet does not have to become Venus like the moment it moves closer to its star than Earth is. Between a temperate state and an extreme state, there are many transitional steps. A planet with bright clouds in a region receiving strong sunlight may reflect some of that energy away. A surface with large oceans may absorb and distribute heat differently from a surface made entirely of dry rock. A slowly rotating planet may form thick cloud systems over the region that constantly receives strong sunlight, reducing the amount of light that reaches the ground. A faster rotating planet may create different wind bands and distribute heat in another way. These details mean that the inner edge of the habitable zone is not an absolute red line. But even with many variables, the underlying principle remains. The closer a planet is to its star, the more energy it has to manage, and if the mechanisms for reflection, distribution, or heat release are not strong enough, surface water will come under increasing pressure. Venus is the example that makes the inner edge easier to understand, although that planet should not be used as a simple copy for every world close to a star. Venus receives more sunlight than Earth, but the terrible heat on its surface does not come only from distance. Its dense atmosphere, rich in carbon dioxide, has trapped heat with tremendous intensity. If we look only at orbital position, we can say that Venus is closer and therefore hotter. That sentence is true, but not enough. What determined the fate of the Venusian surface was the way light and atmosphere worked together over time. Incoming energy was not released efficiently in a way that would allow the surface to maintain liquid water. A rocky world close to Earth in size became a reminder that the inner edge is not only where light is stronger, but where every climate feedback involving water, vapor, clouds, and heat-trapping gases can become highly sensitive. In the opposite direction, the far edge of the habitable zone is connected to a planet receiving too little energy. As the light from the star weakens, the surface more easily becomes cold. Water tends to freeze across wide areas. Ice and snow reflect light very well, causing the planet to absorb even less energy. If that process spreads far enough, a world can slip into a long-lasting frozen state, where liquid water on the surface becomes rare or survives only under special conditions. But the far edge is not simply the beginning of absolute cold. The atmosphere can still change the outcome. Carbon dioxide, if there is enough of it, can help retain heat. A thicker atmosphere can also transport warmth and reduce differences between regions of the planet. So a more distant world may still maintain suitable surface temperatures if it has a strong enough atmosphere, as long as other processes do not push the planet into an unfavorable state. The outer limit is often described by the maximum ability of heat-trapping gases to compensate for weaker sunlight. On a rocky planet with an active carbon cycle, when the climate cools, the process that removes carbon dioxide from the atmosphere through rock weathering can slow down, while volcanoes continue returning some gases to the sky. Over time, carbon dioxide can accumulate and help strengthen the heat-trapping effect. That mechanism is like a slow regulator, operating not through intention, but through the connection between temperature, rain, rock, and air. But the ability to retain heat also has limits. If a planet is too far away, adding more carbon dioxide is no longer enough to make up for the missing sunlight. A thicker atmosphere can also create more clouds or scatter light in ways that make the problem more complicated. At a certain point, a planet has difficulty maintaining widespread liquid water on its surface if it relies only on the ordinary greenhouse effect. Mars sits near the cold edge of this story in the solar system, and its present surface shows how a planet can lose its opportunity. Today, Mars receives less solar energy than Earth, has a thin atmosphere, and has low pressure. Liquid water on the surface cannot last for long in the familiar way of rivers and lakes on Earth. Landform traces still show that water once flowed in the past, but the present is a cold, dry world dominated by ice, dust, and rock. Greater distance placed Mars in a more difficult energy problem. While its small mass, its history of atmospheric loss, and the weakening of its geological processes made that problem even harder to solve. If we only say that Mars is cold because it is farther from the Sun, we miss the deeper part of the story. A more distant planet needs an atmosphere and heat-retaining mechanisms strong enough to resist the decline in light, and present-day Mars no longer holds on to that. When we place Earth between those two directions, the orbital position of the blue planet becomes more meaningful. Earth does not stand in a magical place, completely separate from every danger, but this planet receives a suitable amount of energy for oceans to exist, while its atmosphere is strong enough to hold warmth moderately and thin enough not to turn the surface into an overheated place. If Earth receives significantly more light, water vapor and the heat-trapping effect could become a much larger problem. If it received much less light, ice could expand and make the planet reflect even more energy. Earth's stability does not come from one orbital number being correct, but from the fact that the incoming light lies within a range that other mechanisms can handle. Oceans, clouds, atmosphere, ice, rock, and the carbon cycle all work within that range, allowing liquid water not only to appear, but to persist through most of the planet's history. A more precise way to see it is that distance sets the difficulty level of the climate problem. Closer to the star, a planet has to solve the problem of excess energy. How to reflect enough light, release enough heat, keep water from evaporating too strongly, and avoid feedbacks that cause the surface to warm beyond control. Farther from the star, a planet has to solve the problem of too little energy. How to retain enough heat, prevent ice from reflecting too much light, maintain pressure high enough, and keep liquid water from being locked in permanent ice. In the middle, the problem does not disappear, but the chance of solving it successfully is higher if the other conditions are suitable. The habitable zone, then, is not a zone exempt from risk. It is a region where the energy problem is not yet too extreme, allowing atmosphere and water a chance to create a more durable state. The role of distance also depends on the brightness of the star. A planet at the same distance from its parent star as Earth is from the Sun does not necessarily receive the same amount of energy as Earth, if that star is brighter or dimmer than the Sunday. Around a brighter star, the region receiving suitable energy must lie farther out. Around a dimmer star, that region lies closer in. This is very important when speaking about exoplanets, because many planets have been found around stars smaller than the Sunday. A planet orbiting very close to a red dwarf may not be as hot as first intuition suggests, because the star itself gives off less energy. Conversely, a planet at a seemingly distant orbit may still be hot if its parent star shines strongly. Distance only has meaning when paired with the brightness of the star. Saying how far a planet is from its parent star is not enough. We need to know how powerfully that star shines. The differences among stars also affect the color and type of light a planet receives. The sun gives off much of its light in the range that human eyes perceive as visible light, while cooler stars emit more of their energy in red and infrared wavelengths. Ice, water, clouds, and atmosphere can absorb or reflect different kinds of light in different ways. An icy surface around a cool star may not reflect energy exactly the same way ice does under sunlight from the sunday. A planet's atmosphere also interacts with the spectrum of light in its own way, meaning that the same total amount of energy, distributed differently, can produce different climate outcomes. This is why the modern habitable zone is not calculated only through a rough measure of distance, but also takes into account the type of star, the star's surface temperature, and the way stellar radiation enters the planet's atmosphere. Orbits are not always perfectly circular either. Some planets follow more eccentric orbits, sometimes moving closer to the parent star and sometimes farther away within the same revolution. When that eccentricity is small, the climate system may absorb the change as a kind of orbital season, especially if the oceans and atmosphere can store heat well. When the eccentricity is large, the planet may pass through periods of very strong energy input and then fall into colder intervals, placing great pressure on surface water and the atmosphere. What matters is not only the average energy received across an entire year, but also how that energy is distributed through time. A world that receives enough average energy, but experiences swings that are too strong, may have difficulty maintaining a stable surface environment. Here, distance is no longer a single number, but becomes a rhythm of change between near and far, between heat and cold, between long orbital seasons. The tilt of the rotation axis also changes how light is distributed across the surface. On Earth, axial tilt creates seasons, shifting sunlight between the two hemispheres over the course of the year. If the tilt is very small, the polar regions may remain persistently colder, while the equator keeps a more stable role as the region receiving sunlight. If the tilt is very large, the seasons can become extreme, with one hemisphere receiving prolonged light and then sinking into a period of deep cold. Atmosphere and oceans can soften these differences, but that ability also depends on atmospheric thickness, the amount of water, and rotation speed. Distance from the star determines the total incoming energy, while axial tilt determines where that energy falls and how it changes over time. A planet does not only need to receive enough light, its surface also needs that light to be distributed in a way that does not push large regions into extremes for too long. Rotation speed adds even more layers to the energy problem. A fast-rotating planet has shorter days and nights, helping the surface avoid being heated or cooled for too long in the same place, while also allowing wind systems to form in broad bands. A slow-rotating planet may let the dayside receive energy for longer and the nightside lose heat for longer, forcing the atmosphere to do more work to even out the difference. For planets close to small stars, tidal forces can cause one side to always face the star, while the other side turns away from the light. In that case, the concept of distance still works at the level of average energy, but the surface climate no longer resembles that of a planet with alternating day and night like Earth. Winds, clouds, and oceans, if present, will determine whether heat can be moved from the day side to the night side. Once again, distance lays the foundation for the problem, while whether the world can be habitable depends on how the entire system responds. When scientists speak about the inner and outer edges of the habitable zone, they are not trying to draw a hard fence in space. They are building limits based on certain assumptions: that the planet has a rocky surface, that it has water, that it has some kind of atmosphere, that certain heat-trapping gases are present, that clouds exist or do not exist according to a particular model. Change the assumptions, and the boundaries can shift. A planet with a thick atmosphere is different from a planet with a thin atmosphere. A planet covered entirely by ocean is different from a planet with broad continents. A planet around a cool star is different from a planet around a sun-like star. That flexibility does not make the concept vague or useless. On the contrary, the concept is powerful because it forces us to say clearly what we are assuming. The habitable zone is not a prophecy, but a calculation framework for placing physical conditions within the same picture. This is also why announcements about exoplanets need to be read calmly. When a planet is described as being in the habitable zone, that information is noteworthy, but it only means that the amount of light it receives could be suitable for liquid water under certain conditions. That planet may still have no atmosphere. It may have an atmosphere that is too thick. It may be eroded by radiation from its parent star. It may be a deep water world without an Earth-like rock cycle. It may be a dry, rocky planet, or a world covered in ice. It may have surface pressure that is not suitable. The only certain thing is that the planet has not been ruled out of the search simply because it receives too much or too little light. Any deeper conclusion requires more data, more models, more observations, and more caution. So distance is both important and insufficient. If we ignore distance, we lose the first foundation of planetary climate. If we cling only to distance, we turn a complex system into a circle that is far too simple. A planet needs to stand within a suitable energy range for liquid water to have a chance. But that chance has to pass through many other doors before it becomes a stable environment. Starlight is like the initial supply for every climate process. The atmosphere determines how much of that supply is retained. The surface determines what portion is absorbed or reflected. Water determines how heat is transported and stored. Ice determines whether the planet brightens or darkens beneath the light of its star. Rock and carbon determine whether climate can slowly regulate itself over time. Each factor is connected to the others, and distance is only the place where the first connection begins. When we look at a planet in that way, the habitable zone is no longer an easy label to place on newly discovered worlds. It is the first step in reading the energy history of a planet. How much light has the planet received in the past? Has its parent star brightened over time? Is the orbit stable? Is the atmosphere strong enough to retain warmth, but not so strong that it retains too much? Can water exist on the surface? Or has it been lost, locked away, pushed into vapor, or buried beneath ice? Those answers do not appear all at once, and many of them still lie beyond our present ability to observe directly. But because of distance, humanity knows where to begin. Among the thousands of planets already discovered, worlds receiving a suitable amount of light become more worthy targets to follow. Not because they are certainly alive, but because their physical problem has not yet closed. Distance from the star is like the first line in a planet's climate file. That line tells us how close the planet has been placed to the fire, how much energy it receives, whether it stands more toward the side where water is easily lost, or more toward the side where water is easily frozen. But the following lines tell us what kind of air lies above that world, what pressure rests on the ground, whether water moves between sea and cloud, whether rock helps regulate carbon, whether there has been enough time to maintain stability, or whether a temperate period appeared only briefly before everything changed direction. A habitable planet is not born only from standing in the right position. That position gives the planet only an initial opportunity. The rest is written by the way light meets atmosphere, the way heat meets water, the way ice reflects the sky, and the way a world keeps its balance before a source of energy that can both nourish it and test it. 3 rocky planets in the same star system can share an origin without sharing a fate. Venus, Earth, and Mars are all illuminated by the Sunday. All formed from material left around the young star. All have solid surfaces. All pass through violent eras of impacts, volcanism, gases escaping from the interior, and changes stretching across billions of years. If we look only at simple numbers, we can arrange them in a very neat order. Venus is closer to the Sun, Earth lies in the middle, and Mars is farther away. That order is correct, but it does not tell the most important part. These three worlds are not only 3 points on a measuring stick of distance. They are like 3 vast natural experiments placed side by side within the same planetary system, showing that a rocky planet can move towards suffocating heat, can maintain water and a stable climate, or can become cold and dry, leaving ancient traces of water like faded writing in stone. What gives this trio special weight is that they are not located somewhere completely foreign to human understanding. They belong to the same inner region of the solar system, where planets are mostly made from rock and metal rather than giant amounts of hydrogen and helium. They are not exoplanets that appear only as faint shadows in starlight. Humans have sent spacecraft near them, measured their atmospheres, photographed their surfaces, analyzed soil and rock, and traced the signs of ancient rivers, lakes, and thick cloud layers. For that reason, when we want to understand why the habitable zone is not only about distance, there is no closer or clearer example than these 3 planets. They show that sunlight is only the opening part of the story. The rest lies in how each planet keeps gas, loses gas, keeps water, loses water, forms clouds, builds pressure, and responds to the very source of energy shining down on it. Venus is often called Earth's sister planet because its size and mass are not too different from those of the blue planet. That phrase can easily create a sense of familiarity, as though with only a small change in distance, we might encounter a world much like home. But the more we understand Venus, the more that feeling of familiarity becomes a warning. Beneath its thick, bright cloud layer is a terribly hot surface, pressed under a heavy atmosphere made mostly of carbon dioxide. The pressure on the ground is so great that it no longer resembles any ordinary experience of air on Earth. Heat is trapped so strongly that Venus is hotter than Mercury, even though Mercury lies closer to the Sunday. This makes Venus a very direct lesson. Being closer to the star may place a planet in a risky region, but the atmosphere is what turns that risk into the fate of the surface. If a planet receives more light, water on the surface evaporates more easily. When water vapor enters the atmosphere, it is not only a sign of a wet world. Water vapor also traps heat. Retained heat makes the surface warmer, and a warmer surface pushes more water into the atmosphere. If that feedback loop is not controlled, water can leave the oceans, rise high above the surface, be broken apart by high-energy light into hydrogen and oxygen, and then the light hydrogen can gradually escape into space. A world that once had water, if it slips too deeply into that process, will not merely warm temporarily, but may lose a large part of its ability to keep surface water at all. Present-day Venus is not a direct photograph of every stage that happened in the past, but it shows a frightening possibility for rocky planets. When an atmosphere traps heat too strongly and water no longer plays a stabilizing role on the surface, a world can become something entirely different from the initial image of being almost like Earth. The cloud layer of Venus also reminds us that clouds do not always mean something gentle and cooling, as they often do on Earth. From the outside, Venus reflects a great deal of light and appears bright in the sky, but inside that atmospheric system, the clouds belong to an extreme environment, rich in sulfuric acid, suspended above a heavy and hot layer of gas. Light may be strongly reflected from above, but the heat below is still trapped intensely. This is very important when speaking about habitability, because the same factor can play many roles depending on context. Clouds on a planet can cool by reflecting light, but they can also take part in retaining heat. Carbon dioxide can be a necessary part of helping Earth avoid freezing, but if it accumulates in a dense atmosphere, it can turn the surface into a harsh place. No factor is automatically good or bad. Everything depends on amount, location, time, and the way it interacts with the entire climate system. Earth lies between its 2 neighboring planets, not as a magical balance point guaranteed forever, but as an example of a rare coordination among many conditions. This planet receives enough light for liquid water to exist on the surface, but that light alone does not create lasting oceans. Earth has an atmosphere thick enough to retain some warmth, thin enough for excess heat to still escape into space, rich enough in necessary components to create weather, and stable enough that the oceans are not lost too quickly. Surface pressure allows liquid water to spread into seas, lakes, rivers, rain, and snow. The oceans absorb heat, carry heat through currents, and soften changes between day and night, between warm seasons and cold seasons. Clouds alter how much light is reflected. Ice expands or shrinks with climate, feeding back into the way the planet absorbs energy. Nothing stands alone. Everything continually pulls everything else into a highly complex network of feedbacks. Life on Earth also did not appear on a motionless stage. For most of its history, this planet changed profoundly. The atmosphere transformed. The oceans changed in chemical composition. Ice expanded at times. Volcanoes released gases into the sky. Continents shifted, and photosynthetic organisms altered the amount of oxygen in the atmosphere. If we look only at Earth today, it is easy to imagine this as the natural and already stable state of a planet located in the right zone around the sunday. In reality, that familiar state is the result of a long history in which physics, chemistry, geology, and biology have constantly interacted. Earth is not only fortunate because it stands at a suitable distance. Earth is also large enough to keep an atmosphere, active enough inside to sustain volcanism and long-term tectonics, rich enough in water to create oceans and a rain cycle, and old enough for slow processes to regulate climate across timescales far beyond a human life. One of Earth's most special features is that water does not merely exist, it moves. The ocean is not only a body of liquid beneath the sky. Water evaporates, enters the atmosphere, forms clouds, falls onto continents, seeps into soil, flows through rock, carries minerals with it, returns to the sea, and continues the cycle. Along that journey, water takes part in the way the planet regulates carbon dioxide. Rain and flowing water weather rock, drawing carbon from the atmosphere into compounds that can enter the oceans and sediments. Volcanoes, in the opposite direction, return some carbon to the atmosphere. This mechanism does not work as quickly as an air conditioner in a room, and it is not so perfect that it prevents every climate fluctuation. But over geological time, it helps give Earth a slow thermostat, where rain, rock, sea, and atmosphere all participate in keeping the planet from easily slipping forever toward one extreme. Venus and Mars, placed beside Earth, show how the absence or breaking of those connections can lead to very different outcomes. Mars tells that story in a colder, drier voice. The red planet does not have a thick atmosphere like Venus, nor does it have broad oceans like Earth. Today, the Martian atmosphere is very thin, the surface pressure is low, and water exists mostly as ice or in states that are difficult to maintain as long-lasting rivers and lakes. But the surface of Mars is not completely silent about its past. Dry riverbeds, ancient deltas, minerals formed in watery environments, and landforms once carved by flowing water all suggest that this planet once had wetter periods, perhaps warmer periods, or at least conditions that allowed liquid water to operate on the surface at certain times. What makes Mars compelling is not only that it is cold and dry, but that it seems to have changed. It is like a world that once held part of an opportunity in its hands, then lost many of the conditions needed to keep that opportunity for long. The loss of Mars is connected to many factors at once. This planet is smaller than Earth, so its gravity is weaker, and its ability to hold an atmosphere over long periods is more difficult. Its interior cooled more quickly, geological activity declined, and the ability to resupply the atmosphere with gases became weaker than on a larger, more dynamic world. A global magnetic field, if it once existed strongly, no longer protects the planet in the way Earth is protected today. Solar wind and radiation may have contributed to eroding the atmosphere over time. As the layer of air became thinner, pressure fell, and liquid water on the surface became even harder to sustain. The planet receives less light because it lies farther from the sun, but distance is only part of the problem. If Mars had maintained a thicker atmosphere, richer in heat-trapping gases, and lasting for longer, its climate story might have been different. What the red surface is telling us is that a planet does not only need suitable conditions at the beginning, it needs the ability to protect and renew those conditions across a very long span of time. Mars also shows the difference between once had water and was habitable for a long time. An ancient riverbed is precious evidence, but it does not automatically mean the surface was once like Earth's. Water may flow during brief periods because of temporary climate warming, volcanism, meteorite impacts, changes in axial tilt, or atmospheric conditions different from those of today. A planet may pass through many wet windows and then return to a cold, dry state. For prebiotic chemistry and simple life, those windows may still be deeply interesting, but they are different from a world with stable oceans, a steady rain cycle, and a climate maintained relatively consistently for billions of years. In the search for habitability, this difference is enormous. A temporary pool on a cold, dry planet does not carry the same meaning as an ocean system continuously exchanging with the atmosphere and rock across deep time. The comparison among the three planets also clarifies the role of pressure. On Venus, surface pressure is far greater than on Earth, belonging to a heavy and intensely hot atmosphere. On Mars, the pressure is too low for liquid water to remain on the surface for long. On Earth, pressure falls within a range that allows water to exist widely as a liquid at commonly encountered temperatures. This helps correct a common misunderstanding. Temperature is not the only factor that determines the state of water. Water needs both suitable temperature and suitable pressure. When pressure is too low, water can boil, evaporate, or freeze in ways that prevent lakes and rivers from lasting. When pressure is too high in a strongly heat-trapping atmosphere, the surface can become an environment completely unsuitable for familiar forms of water. Earth holds liquid water not only because it is warm enough, but because the atmosphere creates the pressure conditions that allow water to remain. The atmosphere is the deepest dividing point among the three worlds. Venus has too much heat-trapping gas in a dense system. Mars has too little gas to protect and warm its present surface. Earth has an atmosphere within a range that allows many processes to operate together. But even the phrases too much and too little need to be understood in planetary context. A small enough amount of carbon dioxide can be a necessary part of Earth's climate, helping the planet avoid becoming too cold. A larger amount, in a different context, can lead to a powerful heat-trapping effect. A thin atmosphere may still be enough for some processes on a small planet for a time, but not enough to maintain stable liquid water on the surface. Air, for a planet, is not only an outer covering. It is where energy is retained, where water passes through, where clouds form, where radiation is partly filtered, and where the surface is connected to space. Lose or transform that layer, and the planet's fate changes with it. The surfaces of the three planets also respond differently to light. On Earth, dark oceans absorb a great deal of energy. White ice reflects strongly, clouds change constantly, and continents hold deserts, forests, soil, rock, and snow. The blue planet, therefore, does not have only one way of handling light. Each surface region contributes to the overall energy balance. Venus is hidden by clouds so thick that its surface cannot be directly observed by ordinary sight from outside, and the atmospheric system largely determines how energy behaves. Mars has red dust, polar ice, a thin atmosphere, and a dry surface, so the way it absorbs and loses heat is entirely different. When a planet has oceans, water can store heat very effectively. When the surface is mostly dry rock and the atmosphere is thin, heat can change more sharply between day and night, between highlands and lowlands. The surface is not only where the results of climate appear, it is also a component that helps create climate. Planetary size cannot be ignored either. A small planet has more difficulty holding internal heat for a long time than a larger planet. As the interior cools, volcanism and geological processes can weaken, reducing the ability to return gases to the atmosphere. Weaker gravity also makes the atmosphere easier to lose over long spans of time, especially under the effects of radiation and stellar wind. Mars is a clear example of this vulnerable side of a small planet. Venus and Earth are closer to one another in size, but they show that similar size alone is not enough to guarantee a similar outcome. A planet may be large enough to hold gas, but if its atmosphere moves toward trapping heat too strongly, that size cannot save the surface from extremes. A planet may lie in an interesting energy zone, but if it is too small to hold the necessary layer of air, surface habitability can decline over time. Size is a background condition, not a guarantee. When we place all three planets in the same picture, an important axis appears. Venus represents the danger of excess heat and an atmosphere that traps warmth too strongly. Mars represents the danger of too little atmosphere, too little pressure, and too little ability to hold stable liquid water. Earth is not in the middle, in the simple sense of being an average between two extremes, but in an active state, where incoming energy, outgoing energy, and material cycles are connected to one another. That balance is not a perfect straight line. Earth has been hotter, colder, has passed through ice ages, greenhouse periods, and major biological and geological events. But this planet has maintained liquid water on its surface for an extremely long time, and that is what makes it such an important reference point. Not because every habitable planet must resemble Earth in every detail, but because Earth shows what kinds of connections can help water and climate endure. The lesson from this trio also makes the study of exoplanets more cautious. When a distant planet is found to be close to Earth in size, we cannot yet know whether it resembles Earth or Venus. When a planet lies at a distance where it receives an amount of light similar to Earth's, we cannot yet know whether it has oceans or only dry rock. When a planet shows signs of an atmosphere, we cannot yet know whether that atmosphere is a gentle cloak or a blanket that traps far too much heat. Just by looking within the solar system, we can see how different three rocky planets can be. This helps guard against the rush to call a world an Earth twin. In planetary science, similarity in size, similarity in the amount of light received, or similarity in a few atmospheric molecules are all meaningful pieces of data, but they are not yet evidence of a habitable environment. Venus, Earth, and Mars also tell us that habitability is a historical story, not only a snapshot of the present. A planet may once have had different conditions. Venus may have passed through other climate states before becoming the world it is today, though the details remain a subject of study. Mars almost certainly once had liquid water active on its surface in the past, but it no longer maintains that environment in the way Earth does. Earth itself has not stood still, but has changed through many geological eras. When we look at a planet, we need to ask not only where it is now, but what it has gone through. Has it ever had water? How did it lose its atmosphere? How long did volcanism remain active? How has the parent star brightened over time? Did large impacts change the surface? Questions like these turn habitability into a film lasting billions of years, not a label pasted onto an orbit. At the deepest level, these three planets show that life, if it has a chance, needs a stage more stable than the simple phrase, warm enough, might suggest. On a world that is too hot, complex molecules can be destroyed, water can leave the surface, and the atmosphere can become a wall that traps heat. On a world that is too cold and has an atmosphere too thin, liquid water has no long-term place to stay. Chemical reactions are limited, and the surface faces harsher radiation and more severe changes. On a world like Earth, water can remain, move, dissolve minerals, participate in climate, and create environments where chemistry and biology can develop across very long spans of time. That difference does not come from one single factor. It comes from the layering of distance, mass, atmosphere, pressure, water, geological activity, and time. Leave out any one layer, and the picture becomes too poor. The three nearby worlds around the Sun therefore become three different reminders. Venus reminds us that a rocky planet can be turned into a harsh place by its own atmosphere. Mars reminds us that water can leave traces and then retreat from the surface when pressure and atmosphere are no longer strong enough to support it. Earth reminds us that habitability is not only an initial condition, but the continuous maintenance of many cycles connected to one another. When humanity looks beyond the solar system, searching for planets in the habitable zones of other stars, these three lessons accompany every measurement. They keep us from asking too quickly whether that planet is like Earth, and instead lead us to ask more slowly, more precisely, what direction does its atmosphere resemble? What does its pressure allow? Where is its water? And has its history preserved or erased the most important conditions? Distance from the Sun places Venus, Earth, and Mars at three different energy levels, but atmosphere and water are what turn those three energy levels into three very different surfaces. A closer planet may not only be hotter, but may also be more easily pushed into strong heat-trapping feedbacks if water and atmosphere move in an unfavorable direction. A more distant planet may not only be colder, but may also need a more durable atmosphere to retain heat and keep liquid water. A planet in the middle is not automatically habitable unless its cycles are strong enough to work with the amount of light it receives. In that sense, Earth is not only the beautiful middle point in the solar system, it is evidence that a habitable planet needs long-lasting coordination. Venus and Mars are not only two neighboring planets, they are two ways that opportunity can change direction. When the story returns to the habitable zone, the image of a belt around a star is no longer as simple as it seemed at first. Within that belt, there may be worlds more like Earth, but there may also be worlds more like Venus, or more like Mars, or unlike all three in ways humans have not yet measured. A planet in the right zone can still have its atmosphere turn it into a heat-trapping furnace. A planet in the right zone can still lose its atmosphere and become cold and dry. A planet near the edge of the zone may still be saved for a time by clouds, oceans, or atmosphere. What our three rocky planets teach is not that we should search for a simpler formula, but that we should accept habitability as the result of many layers of conditions operating together. Distance is the foundation. Atmosphere is the way a planet retains and releases heat. Pressure is where water decides whether it can stay. Water is the flow that connects sky to stone. Time is the test of whether everything can endure long enough for a world to truly become livable. A planet does not only have ground. Above plains, craters, oceans, ice deserts, or riverbeds that dried out long ago, there is always a fragile boundary that determines how that world meets the light of its star. That boundary can be thick enough to completely hide the surface beneath. It can also be so thin that it can barely hold on to warmth, letting rock cool very quickly when the sun sets and heat violently when the light returns. In everyday life, atmosphere is easy to understand as air to breathe. But for a planet, it is far deeper than that. It is the middle layer between surface and space, the place where light is filtered, where heat is retained or released, where water is lifted into vapor, where clouds form, where winds begin to move, where pressure presses down on the ground, and where the fate of liquid water is decided in silence. On a world with no significant atmosphere, starlight reaches the surface with almost no buffer. During the day, rock receives heat directly. At night, heat escapes quickly into darkness. There is no wind to carry warmth from one place to another, no cloud to reflect away some of the light, no pressure strong enough for liquid water to remain as lakes or seas in the familiar way. The surface then is almost placed directly into the environment of space, where every change in light immediately becomes a change in temperature. A planet may stand at a seemingly reasonable distance from its star, but if the surrounding layer of gas is too thin or has been mostly lost, that distance is no longer enough to create a stable world. The light may be moderate, but there is nothing to help the surface hold on to that moderation. The atmosphere begins changing the story from the very moment light enters. Part of that light is reflected by clouds, mist, dust, or tiny particles suspended high above. Part of it passes down to the surface, warming rock, oceans, ice, and everything beneath the sky. When the surface warms, it radiates heat back outward, but that heat does not always escape straight into space. Water vapor, carbon dioxide, methane, and many other gases can absorb part of that heat, keeping it near the surface for longer. Thanks to this natural heat retention, Earth does not become a harsh frozen sphere. Oceans can spread, rain can fall, rivers can flow, and climate regions are not pushed too far beyond the range where liquid water can still exist. But that same mechanism, if it becomes too strong, can turn a protective layer of air into a blanket that is far too thick, holding heat until the planet loses the gentle stability it needs. Venus is the clearest image of an atmosphere that is no longer a planet's soft outer garment. From the outside, that planet shines brilliantly, covered by cloud layers so thick that the surface almost disappears from direct view. But beneath that brightness is not a cool world. The Venusian atmosphere is heavy, rich in carbon dioxide, pressing down on the surface with enormous pressure and trapping heat intensely. Sunlight enters, some of it is reflected back, but the remaining energy is held so tightly by that atmospheric system that the ground is hotter than Mercury. Even though Mercury lies closer to the Sun, if we look only at distance, Venus is the planet closer to the Sun than Earth, and therefore hotter. But if we look at the atmosphere, the story becomes more severe. A rocky planet, close to Earth in size, can still move toward an entirely different fate when the layer of gas around it becomes a heat-trapping machine that is far too powerful. The difference between an atmosphere that is just enough and an atmosphere that is too thick does not lie in the presence or absence of a single gas. Carbon dioxide on Earth is not an absolute enemy of life. In its natural amount in the atmosphere, it helps keep the planet warm enough for liquid water to exist widely. Water vapor is the same. It creates clouds, creates rain, takes part in weather, and holds heat. But on a warmer planet, more water evaporates, water vapor rises in the atmosphere, more heat is retained, and that same heat then causes even more water to evaporate. If that loop has no mechanism to restrain it, it can push a world out of a temperate state. A habitable atmosphere is not an atmosphere without heat-trapping gases. It is an atmosphere that retains heat within a delicate enough limit that water neither freezes completely nor is pulled away from the surface too quickly. On the opposite side, Mars shows how an atmosphere that is too thin can cause a planet to lose many things. Its red surface still holds traces of ancient water, dry valleys, fossilized riverbeds, sedimentary regions, and minerals that formed when water was still present. Those traces mean Mars is not a world entirely alien to water. But today, the layer of gas surrounding Mars is too thin, the pressure too low, the temperature too cold, and the surface too dry for liquid water to last as it does on Earth. If water appears, it has difficulty remaining as stable rivers or lakes. It is pushed into ice, vapor, or temporary states under very narrow conditions. Mars reminds us that a planet may once have had water, may once have had wetter periods, but if its atmosphere weakens and no longer provides enough pressure, surface water gradually becomes a memory in stone. Between those two extremes, Earth's atmosphere is not a perfect layer of gas, but a system that is continuously working. It is thick enough to create pressure for liquid water to spread across the surface, rich enough in water vapor for clouds and rain to appear, supplied with enough carbon dioxide to retain part of the warmth, and, in the present era, contains enough oxygen and ozone to reduce the impact of ultraviolet light on the surface. That layer of air does not stand still. It moves as wind, coils into storms, lifts water from the oceans, carries moisture into continents, and pushes warm and cold air masses through different regions. Because of that movement, heat does not remain fixed in the place receiving the most light. The ocean receives heat and releases it slowly. Air moves over seas, over mountains, over plains, carrying water, vapor, and energy with it. A planet with an atmosphere active enough does not only have a sky, it has a way of distributing warmth across the whole surface. Wind is a sign of an atmosphere trying to balance the differences created by light. Regions receiving more energy warm up, air expands and moves. Colder regions draw in other air currents. The planet's rotation bends these flows, creating wind systems, cloud belts, large vortices, and different weather regions. On Earth, this circulation helps prevent the equator, temperate zones, and polar regions from becoming three completely separate worlds. On slowly rotating planets, or planets that always keep one side facing their parent star, the role of wind becomes even more important. One side may receive continuous light, while the other remains in prolonged darkness. Without a strong enough atmosphere, the temperature difference can be severe. With an atmosphere, and perhaps oceans as well, heat can be pulled from the bright side toward the dark side, creating climates far more complex than first imagined. Clouds make that picture even harder to simplify. A cloud can block some of the light, cooling the surface below, but it can also hold in heat, causing the planet to lose warmth more slowly. Low clouds, high clouds, thick clouds, thin clouds, water clouds, acid clouds, clouds on a fast-rotating planet, clouds on a planet with one side always facing its star. Each type affects the heat balance differently. On Earth, clouds are both shade and blanket, both makers of rain and changers of how much light is reflected back into space. On Venus, bright clouds do not save the surface from the terrible heat below. For that reason, when we imagine a distant planet with clouds, we cannot quickly treat that as a gentle sign. Clouds only truly have meaning when placed within the entire atmosphere, along with the temperature, pressure, chemical composition, and amount of light the planet receives. The atmosphere also creates the conditions for water to move. Without a stable enough layer of air, even an ocean, if it exists, has difficulty entering a cycle like Earth's. Here, water does not simply lie on the surface as a mass of liquid. It evaporates, rises into the sky, meets cold air, gathers into droplets, crystals, and clouds, then falls as rain or snow. Rain touches rock, seeps into soil, flows into streams and rivers, carries minerals to the sea, and connects the sky with the planet's crust through quiet currents. This cycle does not only make a planet wetter, it helps transport heat, regulate clouds, weather rock, and draw carbon out of the atmosphere through very slow geological processes. When the atmosphere weakens, the path of water is cut. When the atmosphere is too hot, water may be pushed too high and gradually lost to space. A world with water, but without a suitable atmosphere, will have difficulty gaining the persistent rhythm of circulation that Earth has. Pressure is the quietest part of that layer of air. It does not appear like clouds, does not move visibly like wind, and is not easy to feel when life has grown used to it. But pressure determines whether water can remain on the surface. On Earth, the weight of the atmosphere allows liquid water to be stable in lakes, rivers, and oceans at familiar temperatures. On Mars, low pressure makes liquid water difficult to sustain for long. On Venus, enormous pressure belongs to an atmosphere so hot and thick that the surface no longer carries gentle conditions. Water does not need only the right temperature. Water needs a sky strong enough to hold it in place. Without pressure, simple warmth does not create lasting oceans. If pressure comes with an atmosphere that traps heat too strongly, the planet can be pushed into an extreme environment. Between those two states is the narrow range where water can do its work, flowing, evaporating, condensing, falling, dissolving, and connecting. The layer of gas around a planet is also its first shield against space. Starlight does not only contain the part that warms the surface. It also includes ultraviolet light, X-rays, and forms of radiation that can break molecules apart, change atmospheric chemistry, and harm the fragile structures of surface life. On Earth today, the ozone layer absorbs part of the ultraviolet radiation, helping make the ground less harsh. The atmosphere also causes many small rocky particles from space to burn brightly before reaching the ground, turning them into streaks of meteors instead of intact impact fragments. That protection is not absolute. Large impacts can still happen, strong radiation can still have effects, and an atmosphere can still be eroded over time. But having an atmosphere is very different from leaving the surface, exposed to every influence from space. For planets orbiting small stars, this challenge becomes even clearer. Many red dwarfs are dimmer than the sun, so the region receiving enough warmth lies closer to the star. A planet there may receive just enough light for liquid water, but at the same time it lives closer to the source of radiation and stellar outbursts. If the parent star frequently releases storms of energy, the planet's layer of air must endure long-term pressure. Ultraviolet light can break apart water vapor high in the atmosphere. Light hydrogen can escape into space. Stellar wind can gradually pull gas particles away from the planet, especially if the magnetic field is weak or gravity is not strong enough. A world standing in the right thermal zone can still slowly lose its atmosphere if it cannot withstand the environment of its parent star. Habitability, then, does not only depend on having a sky today, but on whether that sky can survive across a very long span of time. To keep an atmosphere, a planet needs many things working together. Enough mass helps gravity hold gas in place. Internal activity can bring new gases upward through volcanoes and geological processes. Water and rock can pull certain gases out of the atmosphere, preventing them from accumulating too much. A magnetic field, if present, can help reduce the direct impact of stellar wind on the upper atmosphere. But no condition works alone. A large planet may hold too much gas and become a world covered by a thick envelope of air. A small planet may lose gas more quickly. A planet with volcanoes but no surface water will lack an important part of the carbon regulating cycle. A planet with water but an overly violent parent star may still lose a great deal of gas over time. Atmosphere is the result of a long tug-of-war between the planet's interior, the planet's surface, and the star at the center of the system. Earth shows how an atmosphere can become the moving memory of an entire planet. Nitrogen provides most of the background pressure. Oxygen today is tied to the very long history of photosynthetic life. Carbon dioxide moves through volcanoes, rain, rock, oceans, and living things. Water vapor rises and falls with temperature, weather, and the sea. Air does not merely sit above the surface, it continually exchanges with the ocean, the land, life, rock, and sunlight. The present composition of the atmosphere is not something Earth had from the day it formed. It has changed across billions of years, passing through eras with little oxygen, major climate events, and large biological and geological transformations. The familiar blue sky is the result of a very long history, not the default state of every rocky planet at the right distance. This makes the study of exoplanets slower, but also deeper. A distant planet may pass in front of its parent star and allow starlight to skim through its atmosphere. In that very small moment, part of the light carries traces of molecules. From such delicate marks, humans try to read whether that faraway sky contains water vapor, carbon dioxide, methane, or other gases. But an atmospheric sign does not immediately reveal what the surface below is like. Water vapor in the atmosphere does not certainly mean there is an ocean. Methane does not certainly mean there is life. Carbon dioxide does not certainly mean a planet is hot or cold if we do not yet know the amount of gas, the pressure, the clouds, and the orbit. Light offers only a few faint outlines of a sky, while the full climate still has to be assembled from many other pieces. A planet in the habitable zone without an atmosphere is like a promise missing its support. A planet with an atmosphere that is too thick can be pushed to an extreme by that very layer of gas. A planet with a thin atmosphere may not have enough pressure for surface water. A planet with a moderate atmosphere but no water will have no rain, no seas, and no cycle to soften climate through rock and carbon. A planet with water and an atmosphere, but with a parent star that is too violent, may have to fight against prolonged loss. Habitability, once it passes through the atmosphere, is no longer a soothing word. It becomes a fragile state between holding and losing, between warmth and overheating, between cold and thinness, between water remaining and water being pulled away from the surface. If distance from the star gives a planet its first opportunity, the atmosphere is where that opportunity is truly tested. That layer of gas receives light, holds heat, creates pressure, carries water, forms clouds, drives winds, shields against radiation, and records the history of the whole world. It can make a rocky planet gentler, but it can also make that planet harsher. It can keep oceans in place for billions of years, or help push water away from the surface. It can turn starlight into just enough warmth or into a heat trap with no escape. That is why, when we look at a distant planet inside the habitable zone, what matters is not only its position in orbit. What is more worth listening for is its sky. Whether that sky is thick or thin, warm or cold, wet or dry, calm or eroded by its parent star, and whether it is strong enough to preserve the fragile conditions that allow water, rock, clouds, and time to create a world with a real chance. Water does not need only warmth to exist on a planet. It also needs a sky with enough weight to hold it in place. On Earth, this happens so quietly that almost no one notices. The sea rests beneath the sunlight, rain gathers on leaves, rivers flow over stone, water vapor rises and then returns in clouds. And all of those familiar movements depend on something very silent. The air above is pressing down on the surface with just enough weight. Not so lightly that water struggles to remain as soon as it appears, and not so heavily, or so hotly, that the surface is pushed into an unfamiliar state. Between rock, water, and sky, there is a delicate agreement. If that agreement is lost, the same amount of light from the star no longer creates the same world. In everyday life, people often think water changes state, mainly because of heat or cold. Water freezes when the temperature falls, boils when it is heated, and then evaporates into the air. That understanding is correct within Earth's familiar experience, but on the scale of planets, temperature is only half the story. A drop of water resting on stone is also under the pressure of the layer of gas above it. That pressure determines whether it can remain as a lake, a river, or a sea, or whether it appears only briefly before vanishing too quickly. On high mountains on Earth, where the air is thinner, water already boils at a lower temperature than it does at sea level. Even a small change in the thickness of the air around us is enough to make water behave differently. When that change is enlarged into the fate of an entire planet, it can decide whether the surface can hold liquid water for long. Mars is a very quiet but very deep reminder of this. On the red planet, water is not completely absent. Ice still lies at the poles, hidden underground, and the surface still preserves many traces of ancient flows. There are valley floors that look as if water once carved through them, sedimentary regions that suggest old lakes, and minerals that form only when rock has encountered a wet environment. Mars is not a world that has never known water. It is more like a place that once held wet pages in its past, but those pages dried out long ago. Today's layer of air is too thin, the sky too light, and the ground no longer supported enough for liquid water to remain as lasting rivers and lakes. If water appears under certain narrow conditions, it easily evaporates, freezes, or quickly leaves the state needed to create a broad cycle. The dry valleys, then, do not only tell us that water once passed through. They tell us that a planet can once touch an opportunity, and then lose the part of the sky needed to keep that opportunity for longer. Venus stands on the other side of the picture. There, gas is not lacking. On the contrary, The surface is buried beneath a layer of air so thick, heavy, and hot that every gentle image of clouds or sky becomes misleading. The carbon dioxide-rich atmosphere traps heat intensely, presses down on the ground with enormous weight, and turns Venus into one of the clearest examples that having more atmosphere does not mean having temperate conditions. If Mars is like a sky too thin to hold water, Venus is like a sky too heavy, too hot, and too sealed, where the surface no longer has room for liquid water in the familiar sense. Those two neighboring planets place Earth within a rare range of balance. Not an absolute balance, and not an unchanging gift, but a region of conditions where the air is strong enough to hold water in place without becoming an inescapable heat trap. On Earth, the weight of the sky gives water time to do its work. A rainstorm does not simply fall and disappear. Water can gather in soil, move through cracks in rock, dissolve minerals, collect into streams, grow into rivers, cross plains, return to the sea, and then evaporate again beneath the sunday. Those movements require stability. If water appears only for a few brief moments before evaporating or freezing, it has difficulty carving valleys, forming lakes, feeding clouds, wearing down rock, and participating in very slow geological cycles. A planet with fleeting water is very different from a planet where water stays. And that difference does not lie only in temperature. It lies in the layer of air, pressing gently on the ground, enough that each drop is not too easily pulled away by the universe. Liquid water, when it can remain stable on the surface, becomes more than a chemical substance. It becomes a pathway for a planet to exchange with itself. Water connects ocean to cloud, rain to rock, river to sea, atmosphere to solid crust. It carries heat, minerals, and carbon. It creates places where molecules can meet, separate, combine, and pass through increasingly complex reactions. If the sky is too light, that pathway is cut short. If the sky is too heavy and too hot, that pathway is distorted. Only within a suitable range of conditions can water become a long-lasting flow instead of a brief phenomenon. The habitability of a planet, then, does not lie in having a little water somewhere, but in whether water can keep its role in climate, in rock, and in time. The pressure of the atmosphere also helps soften differences across the surface. Air does not simply sit still above the ground. It moves, carrying heat from warm places to cold ones, carrying moisture from oceans into continents, gathering into clouds, forming wind and weather. When the layer of air is thick enough within the right limits, a planet is better able to share energy. Daytime does not so easily become an extreme of heat, and night does not so easily fall into deep cold. Regions receiving more light can pass some of that heat to other regions. Oceans, if present, make the process even gentler, because water holds heat for a long time and releases it slowly. A sky that is too thin weakens these exchanges, leaving the surface to react more directly to each rhythm of light and darkness. A sky that is just enough gives climate not only a covering, but a moving system, quietly reducing the harshness of starlight. This is especially important for planets orbiting close to small stars. Some worlds may always keep one face toward the parent star, while the other side remains in prolonged darkness. If the surrounding layer of air is too thin, the bright side may be heated intensely, while the dark side becomes cold enough for many substances to be trapped in ice. Water and air can be pulled toward extreme states, making it difficult to create a stable surface. But if the planet has a sky that is thick enough and flexible enough, winds can carry heat across the boundary between day and night, clouds can form in regions receiving strong light, and the initial harsh difference can be softened to some degree. On worlds like these, the weight of the air does not only help water remain, it also helps keep the planet from being divided into two halves, too alien from one another. Even so, more is not always better. A thick layer of air can transport heat efficiently, but it can also trap heat too strongly. If the gas composition causes the surface to keep warming, water comes under greater pressure. Water vapor increases in the air. More heat is retained, the surface grows warmer, and then even more water is pushed into the atmosphere. When that loop moves beyond the planet's ability to regulate itself, the ocean is no longer a stable home for water. A world with a thick, hot sky can move toward Venus rather than Earth. So what a planet needs is not as much air as possible, but a suitable mixture of thickness, composition, temperature, incoming light, and surface water. Life, if it must begin with liquid water, needs a measured context more than an extreme. Planetary size also contributes to that moderation. A world that is too small often has difficulty keeping its air for long because its gravity is weaker and its interior cools more quickly, causing geological sources of gas to decline early. Mars shows that direction. As a planet gradually loses its air over time, its surface also gradually loses the ability to hold widespread liquid water. A larger world may hold gas more effectively, but if it holds too much, it can become a planet covered by a thick atmospheric envelope or deep oceans under conditions very different from Earth's. Between those two possibilities lies a difficult search: large enough not to lose its sky too quickly, light enough to still have a clear, rocky surface, active enough for gas and rock to continue exchanging, but not slipping into a state that is too heavy. For exoplanets, this layer of conditions is even harder to grasp. Telescopes can measure the dim shadow of a planet as it passes in front of its parent star, and from that infer its size. They can follow the star's very small motions to estimate the planet's mass. They can read a few signs in the light if the planet has an atmosphere and the signal is clear enough. But the true pressure on the ground does not easily reveal itself. A planet with water vapor in its atmosphere does not certainly have seas below. A planet with carbon dioxide does not tell us by itself whether that layer of gas is thin or thick, warm enough or hot to an extreme. A world close to Earth in size does not necessarily keep an Earth-like sky. It may have lost almost all of its gas. It may hold too much. Its surface, if it has one, may lie beneath a layer of gas or deep water so unlike the kind of environment we are searching for. That is why, when we hear about a planet lying in the habitable zone, the noteworthy point is still only the first step. The amount of light it receives may be suitable, but whether water can remain depends on the weight and composition of its sky. A world with a beautiful orbit, but an atmosphere too thin may not keep rivers and lakes. A world with a clear atmosphere that is too thick may resemble a giant greenhouse. A world that had water in the past, but lost the layer of air it needed, may be left with only dry marks and stone. A world with suitable present conditions also needs to keep them across a very long time, because complex chemistry and life do not grow in a fleeting moment. They need repetition. They need an environment that returns often enough, and they need water not to disappear before reactions have a chance to go farther. On Earth, the ordinariness of water is the most astonishing thing. A wave can reach the shore, a lake can rest quietly through the season, snow can melt into flowing water, vapor can rise and return as rain. All of this happens within a range of conditions that is not too heavy, not too empty, not too hot, not too cold. The sky presses down on the sea with a weight that water can accept. The ground receives light at a level the atmosphere and ocean can still handle. Rock meets rain long enough to be worn down. Carbon passes through slow cycles among air, water, and minerals. Life, after it appears, enters those cycles and makes them more complex. Seen from within, everything seems natural. Seen from the neighboring planets, it is a coordination that is very difficult to repeat simply. Liquid water needs a place to remain. That sentence sounds small, but it contains the atmosphere of an entire planet. Without a place to remain, water is only vapor escaping upward, ice lying still, or a trace of something that once flowed. With a place to remain, water can become sea, rain, river, and an environment for chemistry and time. Distance from the star opens the first opportunity, but the weight of the sky brings that opportunity down to the ground. A planet that wants to keep the gentle stability of water cannot only stand in the right region of light. It needs a layer of air thin enough for light to still touch the surface, thick enough so water does not leave too quickly, soft enough for winds and clouds to operate, and durable enough to resist loss across millions of years. When these things are present together, water is no longer a fragile possibility in a calculation. It can become part of the world, flowing through rock, moving through the sky, and quietly keeping that planet's door open a little longer in the long story of habitability. After there is enough warmth and a sky strong enough to hold it in place, water begins to leave its silent state. It does not only rest in the heart of the sea, does not only gather in a hollow of rock, does not only freeze in cold shadow or shimmer on the surface of a shallow lake. Beneath the light of the parent star, small parts of the ocean rise upward, light enough to leave the waves without a sound. Moisture enters the air, is carried by wind across regions of light and darkness, rises higher and meets the cold, gathers into tiny particles, into clouds, into white veils suspended above the surface. When the clouds become heavy enough, the water returns. Sometimes it falls as rain on a mountainside, sometimes as snow over a cold region, sometimes as a thin mist clinging to stone before the first light of day makes it disappear. From that moment, a planet is no longer only a place with water, it begins to have flow. Flow does not need to be large at first. A small streak of water on rock can find its way down to lower ground. Many small streaks meet and become a stream. The stream moves through soil and minerals, gathers into a river, and the river carries what it touches before returning it to lakes, plains, estuaries, and oceans. Along the way, water does not only change location, it carries heat, salt, eroded grains of stone, and dissolved substances from the continents to the sea. It softens the sharp edges of rock, widens cracks, carves deeper valley floors, leaves behind sediment, and continues moving as though it never tires. Over a single day, that movement may be very small. Over 1,000,000 years, it can rewrite the shape of an entire landscape. A planet with rain and rivers does not only have a wetter scenery, it has a quiet mechanism connecting sky to stone, sea to continent, and the warmth of the parent star to the very long history of the surface. On Earth, these movements happen so familiarly that their strangeness is often hidden. The sea evaporates, clouds form, rain falls, rivers flow, ice melts, groundwater seeps through soil and rock, and everything returns to the ocean in different rhythms. Some rhythms are very fast, like a summer rainstorm pouring down and turning into muddy water, rushing through a mountain town. Some are slower, like groundwater traveling through layers of rock for many years. Some are slower still, like ice accumulating through winter, melting across warming centuries, or the deep ocean storing heat and carbon for spans of time beyond the feeling of a human life. Because many rhythms exist together, the planet does not respond to light like a bare slab of stone. It has delay, memory, and the ability to hold on to part of the energy before releasing it slowly. When water evaporates, it carries heat from the surface into the atmosphere. When moisture condenses into clouds and rain, that energy is released elsewhere, helping the atmosphere distribute warmth among different regions of the planet. A storm over the sea is not only a spinning mass of cloud and heavy rain, it is a way for the ocean to send heat into the sky. An ocean current is not only water moving within the sea, it is a slow pathway carrying warmth from regions that receive more light toward colder places. A layer of snow is not only frozen water, it makes the surface brighter, reflects more light, and preserves the memory of a cold season. In each state, water changes the way a planet receives, holds, and returns energy to space. If water cannot move, the surface becomes far poorer. An ocean resting still beneath a sky without rain would lack a path back to the continents. A layer of ice that never melts would lock water away from reactions on the ground. An atmosphere with moisture but without cycles of falling and flowing would fail to connect clouds with rock. A world with a few briefly wet places is still very different from a world where water returns regularly, season after season, era after era. The durability of water does not lie in the single moment when it appears, but in its ability to come back. Rain must be able to fall many times. Rivers must be able to flow for long enough. Rock must have time to be touched by water, to dissolve little by little, and then to become part of larger cycles of exchange. Rain on a rocky planet is a gentle event, but its consequences can stretch so far that they almost no longer belong to weather. Each drop that falls does not only wet the surface, it begins dissolving minerals, carrying ions along with the flow, moving material from continents to the sea. When water meets silicate-rich rock, some carbon dioxide in the atmosphere can enter slow reactions, eventually being carried into the ocean, sediments, and the planet's crust. Volcanoes, in the opposite direction, can return gas to the sky. No hand controls that process. No machine measures the temperature and turns itself on or off, but over geological time, the meeting of rain, rock, and atmosphere creates a kind of slow regulation. When a planet is warm and rain is more abundant, rock may weather more strongly, drawing some heat-trapping gas out of the sky. When the planet is colder, that process may slow, giving gases from the interior more chance to accumulate. This balance is not perfect, and it does not prevent every fluctuation, but it makes Earth different from a world where sky and stone no longer speak to each other through water. The ocean holds much of that breath. Seawater absorbs heat better than dry rock and does not warm or cool too quickly. Because of this, coastal regions have gentler climates, with less extreme changes between day and night, and softer transitions between warm and cold seasons. Beneath the waves, water currents move according to temperature, salinity, wind, and the shape of the seafloor, carrying energy far from the place where it was first absorbed. The ocean also dissolves gases, stores carbon, nourishes plankton, and returns moisture to the atmosphere. When the sea surface is warm, more water vapor rises, and clouds and rain can change. When the water is colder, that exchange also changes rhythm. The sea is not only where water ends its journey, it is a reservoir of heat, a reservoir of carbon, a source of moisture, a dark mirror that absorbs light, and also the slow memory of climate. Continents give that cycle more edges. If a world were only a deep global ocean, water vapor could still rise and rain could still fall, but the broad contact between atmosphere, rainwater, and continental rock would be weaker. Mountains, plateaus, plains, deserts, forests, and ice-covered regions on Earth create many pathways for water. Rain can fall on newly uplifted rock from tectonic activity. Rivers can wear down mountains and carry material to the sea. Soil can hold water, allowing roots and microorganisms to take part in the chemistry of the surface. Groundwater can move through deeper rock layers before returning to streams or the ocean. It is the alternation between sea and exposed land that allows water not only to cycle through the air, but to enter the planet's crust. A world made blue entirely by ocean may be deeply fascinating, but if it lacks places where water touches rock over long spans of time, an important part of the geological thermostat may operate very differently from Earth's. At the cold poles of a planet, ice preserves water in another language. It does not flow quickly like a river, does not evaporate strongly like a warm sea, but it changes the color and brightness of the surface. When ice expands, the planet reflects more light, absorbs less heat, and may become colder. When ice retreats, darker rock or seawater is exposed, receives more energy, and makes the climate more likely to warm. Ice also preserves traces of older climates in each layer of snow compressed through time. It can trap dust, air bubbles, and signs of distant seasons, then slowly move like a solid river. In that slowness, ice still participates in the water cycle. It stores, delays, reflects, and then returns water when conditions change. A planet with seasonal ice with long-lasting ice but not total freezing, is different from a world locked beneath an endless white layer, with few open regions of liquid water beneath the sky. The right amount of water is just as important as its presence. Too little water, and the surface easily becomes a place where reactions are separated. Flows appear only in fragments, rain is rare, rock is weathered less, and climate has difficulty relying on exchange between sea and sky. Too much water, especially if the entire planet is covered by a deep ocean, and the rock below may be separated from the atmosphere and light, in ways that make the carbon cycle very different from Earth's. At the bottom of extremely deep oceans, pressure may create layers of pressure ice under certain conditions, preventing water from coming into direct contact with the hot rock below. In that case, the planet still has a great deal of water, but the water no longer follows the familiar pathways of rain falling on continents, rivers flowing into the sea, rock being weathered, and carbon entering sediments. A habitable world is not simply the world with the most water. It needs water in the right place, in the right state, with enough opportunity to meet air, rock, and light. Mars holds the missing side of the story. Its ancient valleys and dry deltas show that there was once a time when water flowed strongly enough to leave traces behind. But those traces do not say that the red planet once had an Earth-like cycle for a long time. There may have been warmer and wetter periods. Water may have come from melting ice, from groundwater, from volcanoes, from large impacts, or from eras when the atmosphere was thicker than it is today. What remains on the surface is the memory of movement, not proof of a stable present. As the atmosphere thinned and surface pressure fell, water gradually lost the path that would allow it to become lasting rivers and lakes. Mars therefore carries a very particular scientific sadness. A planet may once have heard the sound of flowing water, but failed to keep a sky durable enough for that flow to continue through deep time. Venus holds another kind of rupture. Its present surface has no gentle seas, no water rain falling onto rock, no rivers carrying minerals out to an ocean. Its heavy, hot atmosphere has brought the planet into a state where water, if it once had a larger role, no longer serves as the one connecting sky to surface as it does on Earth. When water leaves the cycle, a planet loses more than a solvent. It loses the ability to use rain to touch rock, loses oceans that store heat and carbon, loses flowing water that renews landscapes, and loses one of the softest mechanisms for keeping climate from sliding too far. Venus is not only hot because it lies closer to the Sunday, it is hot and dry through an atmospheric history that has taken water out of its central role on the surface. In that comparison, Earth does not appear as the default point, but as the case where water is still allowed to circulate. On planets around small stars, the paths of water may take stranger forms. A tidally locked world may always keep one face turned toward its parent star. The region receiving constant light may form thick clouds, evaporate strongly, and create concentrated zones of rain. The dark side may be colder, with the risk of holding ice or causing part of the atmosphere to condense if the layer of air is too thin. Between those two halves, wind may become a bridge. If the atmosphere is thick enough and water flexible enough, warmth and moisture can be carried across the region of permanent twilight, creating cycles unlike Earth's but still governed by their own order. On such worlds, water does not have to follow the familiar map of seas, clouds, rivers, and mountains to be worth attention. What matters is whether it can participate in a durable system, exchanging with the atmosphere and surface, or whether it is trapped at an extreme that is too hot, too cold, or too dry. Seen from many light years away, those movements are almost impossible to observe directly. Telescopes may search for water vapor in the atmosphere of a planet as starlight passes through the thin layer of gas around it. They may detect a few molecules, measure size, estimate mass, and infer part of the nature of that world. But water vapor in an atmosphere is not the sound of rain. A signal of water is not a river. A distant cloud is not an ocean below. Water may exist as vapor high in the atmosphere, as ice on the surface, hidden beneath the crust, locked inside minerals, or spread across the planet as a deep ocean. Each way of existing opens a different possibility, and many of those possibilities remain hidden by the limits of observation. What humans receive is often only the trace of a sky, while whether water is truly moving across the surface remains a secret behind the signal of light. That caution does not make the story less beautiful. It makes the beauty more precise. A distant planet does not need to be turned into a second Earth simply because it shows a sign of water. Water vapor can be good news, but it can also be a sign of a world losing its ocean if it appears high in the atmosphere within a hot context. Ice can be a precious reservoir, but if it is locked too deeply and for too long, it does not create rivers and rain on the surface. An ocean can be a vast environment for chemistry, but if it does not meet rock and atmosphere through suitable pathways, its ability to regulate climate will be different. Water is always important, but water does not carry the entire answer by itself. It needs a stage made of just enough light, just enough atmosphere, a surface capable of exchange, and enough time for small loops to become history. Within those loops, life on Earth found its way. Before there were forests, birds, mammals, or humans, watery environments were places where molecules met, where minerals came into contact with solutions, where heat, light, and chemistry created many possibilities. Shallow ponds could pass through cycles of wet and dry. Hot springs could bring minerals from the interior up to the surface. Coastlines could receive the rhythm of tides. Oceans could shelter reactions from the direct harshness of the sky. No single setting has been confirmed as the place where life began, but stable liquid water remains at the center of serious hypotheses. And stable water cannot be separated from cycles. There need to be environments that return again and again, changes gentle enough not to erase everything, and flows of exchange long enough for chemistry not to be cut off the moment it begins. A raindrop does not know it is participating in climate. A river does not know it is carrying carbon to the sea. A cloud does not know it is reflecting starlight. But on the scale of a planet, those unconscious movements create the difference between a surface dead and dry, a surface overheated, a surface frozen, and a surface capable of renewing itself. Water is soft, but it has time. It can wear down rock harder than itself. It can pass through the smallest cracks and widen them into deep canyons. It can evaporate from the ocean without leaving a clear mark, then return as rain thousands of kilometers away. It can rest in ice for centuries and then melt into flowing water. The strength of water does not lie in momentary violence, but in its ability to return. A habitable planet needs precisely that ability to return. Not a single wet moment, not a brief season, not a passing trace in stone, but a return durable enough for water to become part of the system. The sea speaks to the sky through moisture. The sky answers with rain. Rain speaks to rock through erosion. Rock answers with minerals and carbon entering the flow. Rivers carry those answers to the sea. The ocean holds them, transforms them, releases them, and then continues sending water vapor upward. Each cycle is very small compared with the age of a planet, but when repeated across millions and billions of years, these cycles create a kind of gentle stability that distance from the star alone cannot provide. Being inside the habitable zone only opens the door for liquid water. That door does not tell us whether water has rain, whether it has rivers, whether it has oceans connected to the atmosphere, or whether it meets rock long enough to regulate carbon. After water can remain, it also has to move. After it moves, it has to return. When that returning flow lasts long enough, a planet begins to look different from a rock that only receives light. It has a sky that can give birth to clouds, a ground that can receive rain, a sea that can send up moisture, ice that can hold the memory of cold, and rivers that can carry material toward deeper places. And within that gentle movement, habitability is no longer a number in an orbit. It becomes the rhythm of water passing through an entire world, quietly allowing rock, air, light, and time to keep meeting one another. When water returns from the sky and touches rock, a planet begins a kind of exchange far deeper than the softness of rain suggests. A drop of water falling onto a mountainside may disappear very quickly to human eyes, sliding across a slab of stone, sinking into soil, joining a stream, and traveling away. But along the way, it carries a small part of the world with it. It dissolves minerals, draws elements out of rock, carries those substances down rivers and into the sea, where they continue entering slower, quieter reactions that stretch across spans of time no longer belonging to daily life. Within these very small movements, carbon dioxide in the atmosphere can also be drawn into a long journey. From the sky, carbon meets rain, meets rock, meets ocean, meets sediment, and may travel deep into the planet's crust before some part of it is returned to the air by volcanoes. No loud sound announces that process. There is no clear boundary between a day of weather and a million years of climate. There is only water, rock, and atmosphere touching one another, little by little, for long enough to change the fate of the entire surface. Carbon dioxide is often spoken of as a heat-trapping gas, but on a rocky planet, it is also a character that moves through many places. In the atmosphere, it absorbs part of the heat radiated by the surface, helping the planet hold on to warmth. If heat-trapping gases like this were completely absent, a world receiving moderate light could still be much colder, and liquid water on the surface would be far harder to maintain widely. But if carbon dioxide accumulates too much, the sky can retain too much heat, pushing the planet toward a warmer, wetter direction, or in extreme cases, out of the stable range for surface water. What matters is that Earth does not only have carbon dioxide in its atmosphere. The blue planet also has pathways that remove carbon from the sky and return it according to very slow rhythms. It is this coming and going that makes carbon part of a climate-regulating mechanism, not merely a chemical component sitting still in the air. Rain begins an important part of that pathway. When carbon dioxide dissolves into rainwater, the water becomes slightly acidic, enough to gradually react with certain kinds of rock on the continents. Rock does not dissolve at once like salt in water. It resists for a very long time, but water also has a great deal of time. Rain falls, water seeps, rivers flow, rock cracks, new surfaces are exposed, and then they continue meeting water and air. Through very slow weathering reactions, carbon from the atmosphere can be carried into dissolved ions, then transported by rivers into the ocean. In the sea, those ions can help form carbonate minerals, the shells of marine organisms, limestone sediments, and many other forms of carbon storage. A portion of the carbon that once lived in the sky is gradually locked into rock, not over a few seasons, but through stacked layers of time. Rain, then, does not only cool the ground, it allows atmosphere and rock to begin exchanging matter. In the opposite direction, the planet's interior is not entirely silent either. Volcanoes and geological processes can return carbon to the atmosphere. Gases released from magma, from subduction zones, from volcanic vents on land, and beneath the sea, bring part of the carbon that has traveled deep into the system back to the sky. That returning rhythm is very slow compared with the rhythm of a rainstorm, but it becomes highly significant on geological timescales. If carbon were only pulled out of the atmosphere and never returned, the planet could cool in another direction. If carbon were only delivered into the atmosphere, without rain, rock, and oceans drawing some of it down, the sky could accumulate heat-trapping gas too strongly. Long-term stability lies in the dialogue between the two directions. Water and rock pull carbon out of the air, while the planet's interior returns some carbon back. The two do not balance perfectly every year or every century, but across very long spans, they can help keep climate from easily falling forever into one extreme. This mechanism is gentler than any machine humans can imagine because it does not operate by command. When a planet grows warmer, more water evaporates, rain may become stronger in many regions, and reactions between water and rock may happen faster if there are continents, suitable rocks, and broad enough flows. As weathering increases, more carbon dioxide is removed from the atmosphere, reducing some of the sky's ability to retain heat. When a planet becomes colder, rain may weaken, ice may cover more land, liquid water may have less contact with rock, weathering may slow, while volcanoes may continue adding carbon to the atmosphere. Across long periods of time, carbon dioxide may rise again and help retain more warmth. This feedback is not magic, and it is not enough to save every planet under every condition, but it gives Earth a kind of climate resilience. The planet can be pushed off balance, but there are slow processes that pull it back toward the range of liquid water. Within that slowness, there is a beauty of its own. A rainstorm falling today does not make the planet's temperature change immediately. A river carrying minerals to the sea does not make the atmosphere lighter in one night. A layer of limestone forming on the seafloor does not change the sky by itself. But when these small events repeat for millions and hundreds of millions of years, they become part of climate history. Earth has not kept its oceans for so long only because it stands at a suitable distance from the sunday. It also has the ability to carry carbon through very long cycles among air, water, rock, and the interior. Because of this, when the young sun was dimmer than it is today, the atmosphere may have been different. As the sun has gradually brightened with age, geological and biological cycles have also helped the climate change. A habitable planet does not only solve the problem of today, it has to travel with its star through time. This makes continents more important than they may appear. Exposed land is not only where mountains, forests, deserts, or rivers exist. It is where rain can meet rock directly beneath the atmosphere. Every newly uplifted mountain range exposes layers of rock that have not yet been weathered, opening more surface for water and carbon dioxide to touch. Every large river carries material from inside the continent out to the sea, connecting highlands to oceans through a slow chemical flow. If there are too few continents, the amount of rock exposed to rain and atmosphere may be reduced. If the continents are too dry, there may not be enough water to carry the reactions far. If the surface is covered too widely by ice, rock is sealed beneath it, and weathering weakens. The presence of exposed land, rain, and flow creates a network of exchange that a completely dry rocky planet, or a world covered entirely by deep ocean, may not have in the same way. The ocean receives that carbon as a vast but complicated reservoir. Seawater dissolves gases, nourishes tiny organisms, creates an environment where minerals can precipitate, preserves sediments, and continually exchanges with the atmosphere. Plankton, corals, bacteria, and many other forms of marine life on Earth have taken part in the way carbon moves through the ocean, forming shells, sinking, being buried, or returning through biological and geological cycles. Before life made everything more complex, the ocean could still be a place where chemical reactions occurred on a large scale. After life appeared, the sea became part of a far more living carbon cycle, where organisms did not only adapt to climate, but gradually changed climate itself. But even if we set life aside, the exchange among seawater, atmosphere, and rock remains an important axis for long-term stability. Volcanoes often call to mind violent images, but in the carbon cycle, they have a slow and enduring role. When molten rock rises, gases held in the deep interior can escape. Carbon that was once buried in sediments or carried down into deep regions through tectonic activity can return to the sky after very long journeys. A planet that has cooled completely, with no significant geological activity left, may gradually lose the ability to replenish its atmosphere with gases. Then, if carbon is locked into rock and never returned, or if the atmosphere is eroded by the parent star without any replacement source, the surface may slide away from a once suitable state. Conversely, a planet with strong volcanism, but without mechanisms to pull carbon out of the atmosphere, may accumulate too much heat-trapping gas. Internal activity, then, is not only the foundation for volcanoes and earthquakes, It is part of the long breath between the planet's interior and its sky. Plate tectonics, if present, makes that exchange cycle deeper. On Earth, crustal plates move slowly, building mountains, opening oceans, pulling sediments into deep regions, and returning material through volcanoes. That rhythm is so slow that within one human life, it is almost invisible, but it helps keep carbon from being trapped forever in a single layer. Rock is weathered on the continents. Material enters the sea. Sediment is buried. Crustal plates sink downward. Carbon travels deep, and some of it returns through volcanic activity. Not every habitable planet necessarily needs plate tectonics exactly like Earth's, and science still has many uncertainties about possible alternative pathways. But a planet needs some form of long-lasting exchange between atmosphere and interior if it is to maintain a surface climate for a very long time. A surface that remains still for too long may gradually lose its ability to regulate. An interior that becomes too quiet may leave the sky without a needed source of renewal. When life enters that cycle, everything becomes more subtle and more difficult to separate. On Earth, photosynthetic organisms take carbon dioxide from the atmosphere and water, use light to create organic matter, and return oxygen to the sky through a very long history. Plants, soils, microorganisms, marine life, the carbonate shells of many species, organic sediments, and the entire biosphere have made carbon move not only through rock and water, but through living bodies. Forests hold carbon in trunks, roots, and soil. Oceans hold carbon in plankton and deep water. When organisms die, some carbon returns to the air, while some sinks and is buried. Life did not create the carbon cycle from nothing, but it changed the speed, pathways, and distribution of carbon. This makes present-day Earth very different from Earth before life transformed the atmosphere. Even so, in the search for habitable planets, we should not require life to appear first before a stabilizing mechanism can exist. Before biology takes part, a planet still needs non-biological pathways for atmosphere, water, and rock to exchange with one another. Without rain, without exposed rock, without oceans, or without internal activity, long-term stability may be weaker. Life, if it ever has a chance to begin, may need a surface that has already remained stable for a long time before it can begin to act back upon its environment. In other words, carbon, rain, and rock are not only the background of a living planet. They may be the conditions that prepare the stage, keeping liquid water, temperature, and chemistry from disappearing too soon. Too little water makes that stage difficult to operate. If a planet is arid, with rare rain, weak flow, and little weathering of rock, carbon dioxide has difficulty being drawn out of the atmosphere through the familiar pathway. The surface may still have minerals, still have gases, still have light, but the exchange between atmosphere and crust becomes slower or more fragmented. Carbon from volcanoes may accumulate if there is not enough water and rain to carry it into rock and ocean. Conversely, if the atmosphere is lost while water is also scarce, the planet may slide toward a cold, dry state like present-day Mars. Water is not only an environment for chemistry, it is also the transporter. Without water, the components of a planet have fewer chances to meet. The atmosphere remains above, rock stays below, carbon is trapped on one side of the system, and the surface loses much of its ability to regulate itself. Too much water does not necessarily create a better state either. A planet covered entirely by a very deep ocean may lack exposed continents where rain can touch rock beneath the sky. If the water is too deep, pressure at the seafloor can create conditions that, in some cases, prevent direct exchange between the ocean and the rock below. Without exposed land, without rivers carrying minerals from continents to the sea, without mountains widely weathered by rain, the carbon cycle may follow a very different path. A water world may still have chemistry, still have an ocean, and still have interesting environments on the seafloor if there are sources of heat and contact with rock, but it does not automatically have an Earth-like climate regulator. Surface habitability may require a more difficult mixture, enough water to flow and evaporate, but not so much that rock and atmosphere are separated from one another. That just enough is not a simple number. It depends on planetary size, gravity, rock composition, ocean depth, the amount of atmosphere, the brightness of the parent star, the rate of water loss, and impact history. A planet with less water than Earth may still maintain a cycle if the water is well distributed, the atmosphere is suitable, and enough continental land meets the rain. A planet with more water than Earth may still have other mechanisms of exchange, but it cannot be quickly treated as a blue copy of home. On the scale of the universe, water is something to notice, but the distribution of water is what makes the difference. Water on the surface, water in the atmosphere, water in rock, water beneath ice, water in a deep ocean. Each place gives water a different role. Only when water can connect many layers of the planet does it become part of a long-lasting mechanism of stability. Carbon also does not automatically keep a planet in a perfect state. There were periods when Earth passed through very cold climates, with ice expanding strongly, and there were also periods that were much warmer. Volcanoes, weathering, oceans, ice, living things, and orbit all change over time. So climate is never a calm straight line. The carbon regulator is not like a lock holding temperature at one fixed level. It is more like a slow elastic system, one that can help a planet avoid being trapped forever in certain extremes, while still allowing large fluctuations. This matters because habitability does not require everything to remain as gentle as a spring day. It requires conditions not to be broken for so long or so deeply that liquid water and complex chemistry lose any chance of returning. A planet can endure change as long as there is still a pathway toward recovery. Venus shows what happens when that pathway no longer leads back to a gentle state. If surface water is lost and the atmosphere traps heat too strongly, water rain no longer falls onto rock, Earth-like weathering no longer works in the familiar way, and carbon is no longer drawn out of the atmosphere through the same network of seas, rain, and continents. The sky becomes thick and hot, the surface dry, and the feedbacks carry the planet into a very different state. Mars shows the opposite direction, where the air is thin, surface water is difficult to sustain, and rain and rivers no longer have enough strength to connect rock with atmosphere as they once may have. A planet that loses water, loses air, or loses geological activity may still preserve traces of the past, but the cycles of exchange that help make climate more durable have weakened. Between those two lessons, Earth has kept its complexity not because it avoids every fluctuation, but because many cycles of exchange are still working. When we look at exoplanets, the hardest part is that these cycles of exchange are almost completely hidden. Telescopes may find signs of carbon dioxide in an atmosphere, but they cannot immediately know whether that gas is being supplied by volcanoes or being pulled down into rock by rain. They may find water vapor, but they cannot see rivers flowing across continents. They may measure size and mass, but they do not necessarily know whether there is plate tectonics, volcanism, shallow oceans, exposed continents, or rock undergoing weathering. A distant planet may have a carbon dioxide-rich atmosphere because it is cold and needs to retain heat, or because it has moved toward overheating, or because there is no cycle strong enough to remove carbon. The same molecule in light can carry many different stories. To understand a planet, we need to know not only which gases are present, but where those gases are going, where they are being added from, how they are being removed, and whether that exchange cycle can endure. This makes the concept of the habitable zone deeper with each layer. Distance provides suitable energy. Atmosphere holds or releases heat. The weight of the sky allows water to remain. The water cycle lets water move through clouds, rain, rivers, and seas. Then carbon, rain, and rock determine whether the climate has a slow way of regulating itself in response to major changes. A planet can stand at the right distance and still have no rain touching rock. It can have rain, but not enough broad continents. It can have an ocean, but one separated from rock. It can have volcanoes, but no water to draw carbon down. It can have carbon dioxide, but too much or too little. Each condition opens another door, and each door can close if the remaining connections are missing. Earth is not the only model the universe can create, but it is the nearest story showing how many cycles of exchange long-term stability can require. Rain falling onto rock does not only wet a mountainside, it begins a journey that carries carbon out of the sky. A river does not only flow toward the sea, it carries continental material and connects reactions on land with ocean chemistry. A volcano does not only release fire, it returns gases from deep within the planet to the atmosphere. The ocean is not only blue, it stores heat, stores carbon, nourishes life, and slows the planet's rhythm of change. These processes are not loud, not fast, and not easy to see in a single moment. But over long spans of time, they create a climate foundation durable enough for liquid water not only to exist, but to become an environment where life can develop and transform its own sky. A habitable world needs more than the luck of position. It needs pathways of return. Carbon must have a way out of the atmosphere when the sky holds too much heat. It also needs a way back when the planet grows cold. Water needs rain to meet rock, rivers to carry material, seas to store it, and an atmosphere through which to return. Rock must be exposed enough to react, but the planet's interior also needs to remain active enough not to cut off the long-term source of gases. All of this happens so slowly that a civilization could look up at the sky for an entire lifetime and never see it. But that slowness is exactly what can travel with a planet across billions of years. Habitability is not only the moment liquid water appears beneath starlight. It is the ability to keep those cycles of exchange going, so the surface is not abandoned in extreme heat, extreme cold, drought, or geological silence for too long. After the cycles of rain, rock, and carbon, the image of a temperate planet becomes less simple, but also more alive. It is no longer a sphere placed neatly inside a region of light. It is a world exchanging with itself. The sky sends rain down to the ground sends minerals to the sea holds gases and heat, rock buries carbon, and volcanoes return the deep breath of the interior upward. Each cycle can weaken, strengthen, break, or change direction. A habitable planet does not need everything to remain unchanging. It needs enough connections that when one part changes, the other parts still have a way to respond. In that slow response, climate may not be perfect, but it has a chance to endure. And in places where water still falls onto rock, carbon still passes through the sea, and volcanoes still return gases to the sky, a world may preserve its gentle stability far longer than any beautiful distance around a star could promise by itself. The cycles of exchange among rain, rock, carbon, and ocean can help a planet keep a gentle stability for a long time, but no cycle operates alone in empty space. At the center of every planetary system, there is always a source of light that is changing, releasing energy in every direction, and aging according to its own rhythm. A planet may have seas, clouds, a layer of air that is just enough, rock undergoing weathering, and volcanoes returning carbon to the sky. But all of those things still have to live with the temperament of the central star. The star's light can be steady enough to nourish a durable climate. It can also be too violent in its youth, with too much radiation, too many flares, and too many invisible streams of particles striking the atmosphere. The light source that opens the opportunity for liquid water can also be the source that breaks water apart, erodes the atmosphere, and gradually strips the surface of the protection it needs. A star does not only shine, it blows into space. From its blazing outer regions, charged particles continually stream outward, forming stellar wind. Along with the visible light that warms the surface, a star also emits ultraviolet radiation, X-rays, and many higher energy forms of radiation. The gentler part of the light helps water evaporate, clouds form, green plants on Earth photosynthesize, oceans absorb heat, and climate gain the energy it needs to operate. The harsher part can break apart molecules in the upper atmosphere, alter the chemistry of the sky, and gradually push light gas particles outward into space. A planet does not only need to stand in the right place to receive enough warmth, it also has to endure the sharp edge of starlight, the part that does not appear as golden light on water, but still quietly acts on the thin layer of air around that world. The sun seems stable to Earth because, within a human lifetime, it rises and sets with such familiar rhythm that it feels like an unchanging foundation. But on the timescale of planets, even the sun does not stand still. When it was young, it was more active in many ways, with stronger stellar wind and more intense high-energy radiation than it has today. Over the long term, as a sun-like star progresses through its life, its brightness also gradually changes. Earth has had to travel with a light source that is not completely fixed, and slow climate exchange cycles such as carbon, rock weathering, oceans, and clouds have helped keep the surface from leaving the range of liquid water too early. Earth's habitability is not simply the story of a planet standing in the right orbit at one moment. It is the story of a world learning to keep its balance while its star also quietly changes rhythm across billions of years. Starlight first acts through the amount of energy a planet receives. A brighter star pushes the region where liquid water can be maintained farther outward. A dimmer star pulls that region closer in. In a simple view, it is like changing position around a fire. If the fire is strong, you stand farther away. If the fire is weak, you stand closer. But a star is not an ordinary fire, and a planet does not merely stand there receiving warmth. If it orbits close to a small, dim star, the planet may receive a total amount of energy similar to Earth's, but that close distance exposes it to other effects as well. Stronger tidal forces, a higher chance that one side always faces the star, and stellar winds and outbursts that may reach the atmosphere with greater intensity. A region of just enough light is not automatically a region of calm. It only says that the heat may be suitable, while whether the parent star's environment is gentle enough for the planet's sky to survive for long still has to be examined. Stars that are smaller, cooler, and dimmer than the sun hold a special attraction in the search for potentially habitable worlds. They are very common in the galaxy. They live for a very long time, and because the region that receives enough warmth lies close to the star, planets orbiting them are easier to detect with many of today's observing methods. When a planet passes in front of a small star, its shadow blocks a larger portion of the star's light than it would if it crossed in front of a large star. Because of this, planetary systems around red dwarfs have become places where humans have found many noteworthy targets. But that very closeness also creates a challenge. Many red dwarfs, especially when they are young, can release powerful flares, causing ultraviolet radiation and X-rays to surge for short periods. For a planet orbiting very close, each event is not only a brighter flash in the sky, it is a disturbance reaching the upper atmosphere, touching water, vapor, molecules, and the ability to keep a protective layer of air. Ultraviolet radiation has two sides. A certain amount can provide energy for complex chemical reactions, helping create prebiotic pathways in some environments. But too much ultraviolet radiation can break apart fragile molecules and make the surface more difficult for unprotected life. On Earth today, the ozone layer reduces the harmful ultraviolet radiation reaching the surface. But that ozone layer is tied to a history of atmospheric oxygen produced by living organisms, not something present on every young planet. A newly formed world without that kind of protection, if it orbits close to an active star, may have to face a sharper, stronger, and less forgiving sky. Surface water, if it evaporates high into the atmosphere, can be broken apart by high-energy light. Light hydrogen can gradually escape into space, while oxygen may remain or take part in other chemistry. Over long spans of time, these small losses can drain oceans or deeply change the atmosphere. Stellar wind is also a flow invisible to ordinary sight, but powerful in its effects. Charged particles stream outward from the star, meet the uppermost layers of a planet's atmosphere, transfer energy, pull gas particles away, heat the upper atmosphere, and under certain conditions contribute to atmospheric erosion. A planet with a global magnetic field can deflect part of that particle stream, adding another layer of protection. Although a magnetic field is not an absolute shield, Earth has a magnetic field and an atmosphere thick enough to shelter the surface from many direct effects. Present-day Mars no longer has a strong global magnetic field like Earth's, and it has a thin atmosphere, making its history of atmospheric loss a nearby lesson in the fragility of a planetary sky. A world orbiting close to its parent star, receiving a suitable amount of heat but constantly being eroded by stellar wind, may not keep surface conditions long enough for water and chemistry to go far. For a planet to keep its atmosphere against the influence of its star, it needs many things at once. Gravity must be strong enough to hold gas molecules. The upper atmosphere must not be heated too intensely. A magnetic field, if present, can help reduce some particle streams. Geological activity can replace some lost gases through volcanoes and internal processes. Oceans and rock can pull certain gases out of the sky, preventing excessive accumulation. But if the parent star is too violent for too long, these mechanisms may not compensate for the loss in time. If the planet is too small, gas escapes more easily. If it is too close to the star, the upper atmosphere is affected more strongly. If water is carried high, and its molecules are broken apart again and again, the oceans can gradually lose their lightest component. A habitable sky, then, is not only something a planet is born, it is something that must be preserved through a long trial with its own source of light. The youth of a star is especially important. Many stars are more active in radiation and flaring when they are newly formed. For small stars, the stage before settling into stability can last a long time, while the region receiving enough warmth is still changing, and nearby planets may have to endure much higher energy than they will later. A planet that now lies within a suitable region of light around a small star may in the past have passed through an overheated phase, when water was pushed strongly into the atmosphere and more easily lost to space. If that world lost most of its water early on, being in the right zone later does not automatically bring oceans back. Habitability may sometimes be decided before the planetary system becomes calmer. A planet does not only need moderate conditions in the present, it has to survive the violent youth of its star. Sun-like stars tell a different story. They do not live as long as red dwarfs, but they have a stable phase long enough for planets at suitable distances to maintain surface climates for billions of years. The Sun has given Earth time, not completely peaceful time, because the blue planet has still passed through impacts, volcanism, ice ages, atmospheric changes, and major extinctions, but the central light source has been stable enough that liquid water was not erased from the surface early on. That stability matters deeply. Complex chemistry needs time. Simple organisms need time. Oxygenating the atmosphere needs time. Multicellular life needs time. A star that lives too briefly or changes too quickly may not give a planet the chance to pass through those slow steps. A star that is too violent or too close may also strip away the atmosphere before time can become an advantage. Stars larger than the Sun shine more strongly and usually have shorter lives. The region where liquid water can be maintained lies farther away, but the star's development happens more quickly. A planet may receive the right amount of energy for a time, but the stable window may be narrower. If life needs billions of years to move from simple chemistry to complex ecosystems, the lifetime of the star becomes an important factor. Stronger light does not only push the habitable zone outward, it also comes with a different rhythm of stellar evolution, one in which the energy source changes more quickly over time. When searching for a world with long-term surface stability, we cannot ask only whether the planet stands in the right place today. We need to ask whether the star is durable enough, long-lived enough, and free enough from violent instability for the planet to keep its oceans, atmosphere, and carbon cycle across deep spans of time. The color of a star's light also makes a planet's surface respond differently. A cooler star emits more of its energy in red and infrared wavelengths. Ice, water, clouds, and atmosphere do not absorb or reflect every kind of light in the same way. Ice under the light of a cool star may not reflect energy exactly like ice under sunlight from the Sunday gases in the sky also select different wavelengths, causing heat to be absorbed at different layers. Because of this, two planets receiving the same total amount of energy can still have different climates if their light sources have different colors. A star does not only determine the amount of light, it determines the kind of light that enters the atmosphere, and that kind of light affects clouds, ice, water vapor, chemical reactions, and the way the surface is warmed. This makes ice and clouds into partners in conversation with the star. On Earth, ice strongly reflects sunlight, helping cold regions preserve their coldness. But around a redder star, ice may absorb more of the infrared energy, causing the ice-light feedback to behave differently. Clouds also change their role depending on the color and intensity of the light. A thick cloud layer over a region receiving strong sunlight may reflect some energy away, protecting a planet near the hot edge. But if clouds retain heat too well, or if water vapor increases too much, that protection may weaken. When the light source is different from the sun, Earth's familiar feedbacks cannot simply be carried over unchanged. Each star system has its own way for light to touch the sky and surfaces of the planets around it. The parent star also shapes the rhythm of seasons in indirect ways. Its gravity keeps the planet in orbit, but interactions with other planets can make the orbit slightly eccentric, change the tilt of the rotation axis, or make seasons stronger over long periods of time. If the orbit is too eccentric, the planet may sometimes come closer to the star and receive more energy, then move farther away and become colder. Oceans and atmosphere can soften that fluctuation, but only within limits. If the energy source changes too strongly across orbital seasons, water may be pushed through states that are difficult to stabilize, evaporating heavily during the close approach, then freezing widely during the distant phase. A star is not only the average light over an entire year, it is the center of a gravitational rhythm, where distance, season, axial tilt, and orbit all determine how energy reaches the surface. Planets close to small stars also experience stronger tidal forces. Over time, those forces can slow the planet's rotation, pulling it toward a state where one side always faces the parent star. Then the star no longer rises and sets across the whole surface in the familiar way. One region may always receive light, another may remain long in darkness, and between the two halves lies a transition zone where winds, clouds, and water have to work intensely to share heat. This opens a different kind of climate, not necessarily hopeless, but certainly not as simple as the image of a freely rotating planet with regular day and night. In that case, the light source does not only determine the amount of heat, it fixes the geometry of light upon the surface, forcing the atmosphere and oceans, if present, to find their own way to connect the two sides of the world. But even a violent star does not make every planet around it hopeless. Habitability is always the result of many factors responding to one another. A planet with a thicker atmosphere may endure some losses better. A strong magnetic field may help reduce the impact of stellar wind. A deep ocean may shelter chemistry from surface radiation. Thick clouds may reflect some light away from regions receiving strong illumination. An active interior may replace gases that have been lost. If water lies beneath ice or below the surface, that environment may depend less on direct starlight. Each possibility has limits, but they remind us that the parent star does not write a planet's fate alone. It presents the challenge, while the planet responds with mass, atmosphere, magnetic field, water, rock, clouds, and time. Earth has the advantage of a star stable enough and a planet dynamic enough. The sun is not so small that the habitable zone lies pressed close into an environment of intense tides and nearby flares, and not so large that its stable life is too short. Earth is large enough to keep an atmosphere, wet enough to have oceans, active enough inside to maintain the carbon cycle over long periods, and magnetized enough to reduce many direct effects of the solar wind. No single factor creates a habitable surface on its own. But when they work together, sunlight becomes an energy source processed by the planet through many layers. The atmosphere filters and holds heat, clouds reflect, seas absorb, rock weathers, carbon cycles, and later life changes the sky itself. Earth's gentleness does not lie only in a gentle sun, but in the long coordination between the light source and the world receiving that light. Venus and Mars show how those forms of coordination can drift away. Venus receives more energy, its atmosphere traps heat more strongly, water no longer plays a surface role as it does on Earth, and the planet has become a hot, thick, dry world at the ground. Mars receives less energy, is smaller, has lost more atmosphere, no longer keeps surface water stable, and its ancient flows remain only as traces. Both orbit the same Sunday. That makes the lesson clearer. Even when the parent star is a familiar source of light, each planet can still respond in very different ways. When the light source changes to another kind of star more violent, smaller, redder, brighter, shorter lived, or more active, the diversity becomes far greater. The habitable zone cannot be separated from the nature of the star that creates it. In the search for exoplanets, the parent star is often something humans know more clearly than the planet. Starlight reveals temperature, size, relative mass, age, activity level, flares, and sometimes chemical composition. The planet appears only indirectly, through a dimming shadow, through a gravitational tug, or through a few thin signs in the light. So to understand a small world, we first have to read the star. If the parent star is too active, the planet's atmospheric signal may be noisy, and the atmosphere itself may be at risk. If the parent star is calmer, the planet has a better chance of keeping a stable layer of air, but it still needs enough evidence about pressure, water, and surface conditions. A star does not only illuminate a planet, so telescopes can detect it. The star is also the planet's environmental record, a place holding many clues about the trials that small sky has endured. There are worlds around red dwarfs that draw great interest because they are close to Earth in size and receive an amount of light that may be suitable for liquid water. But alongside that attraction are questions that remain open. Do they still have atmospheres? If they do, how thick are those layers of air? Was there water lost when the parent star was young and highly active? Do flares alter atmospheric chemistry too often? Does one side always face the star? Are clouds and winds strong enough to distribute heat? What role does a magnetic field play? These questions do not make small star systems less interesting. They make them rich natural laboratories, where habitability may differ from Earth's in many directions, and where every atmospheric signal, every sign of water or carbon, must be placed within the light of the parent star. A planet around a sun-like star is not automatically safe either. If it lies a little closer, water may come under greater pressure as the star brightens over time. If it lies a little farther out, the atmosphere has to retain heat more effectively to resist the cold. If the orbit is unstable, seasons of energy can become extreme. If the planet is smaller, the atmosphere may be lost more quickly. If there is not enough geological activity over a long period, the carbon cycle may weaken. A sun-like star gives humans a familiar standard for comparison, but it does not replace the entire history of the planet. Even within the solar system, 3 rocky planets are enough to prove that. The same light source does not create the same fate. And with other stars, each source of light sets a different set of conditions that a planet must live with. Across very long spans of time, the habitable zone itself does not stand still. As a star gradually brightens, the region receiving enough energy for liquid water can shift outward. A planet that once lay in a temperate zone can slowly move closer to the hot edge without changing its orbit at all. A planet that was once too cold farther out may receive more energy later. Habitability can therefore be a window that opens and closes, or one that remains closed in youth and opens more as the star changes. But water, atmosphere, and carbon are not always waiting there to take advantage of that window. If the planet has already lost its water, later warming will not recreate oceans. If the atmosphere has been eroded too much, a more beautiful thermal orbit is still not enough. If the surface has entered an extreme state, the path back may be very difficult. A planet needs not only the right conditions in the present, but a history favorable enough that when opportunity arrives, the necessary ingredients are still there. This makes habitability more like a companionship than a fixed position. The planet orbits the star ages, the atmosphere changes, water is lost or preserved, volcanoes grow strong and then weaken, rain weathers, rock, carbon enters and leaves the sky, ice expands and retreats. All of these processes both respond to starlight and change the surface conditions themselves. A gentler star cannot replace an atmosphere. A good atmosphere cannot fully resist a parent star that is too violent. A broad ocean cannot last if water is gradually lost to space. A slow carbon cycle needs time, but time is only useful if the star allows the planet to keep its stage. Habitability is therefore the durable overlap between the rhythm of the star and the rhythm of the planet. The light of a star may look quiet from a safe distance, but for a planet orbiting close to it, every ray of light, every stream of particles, and every flare becomes part of the climate. A world can be warmed by the very source that once eroded its sky. An ocean can remain liquid thanks to stellar energy, but can also gradually be lost if water vapor is pulled high and broken apart. Clouds can be born from warmth, but must also resist overheating. Carbon can help retain heat when the star is still dim, and then needs to be drawn down when the star becomes brighter. There is no simple boundary between nourishment and trial. The parent star is at once the heater, the wind, the source of radiation, and the long clock of every planet around it. When we look at a world inside the habitable zone, what we need to hear is not only how much light it receives, but what kind of star that light comes from. Is the star young or old, calm or violent, brightening slowly or quickly, emitting much ultraviolet radiation or little, flaring often or rarely, living long enough or opening only a brief window? Is the planet's sky durable enough to survive its earliest years? Did its water survive the star's restless youth? Was the atmosphere replenished after loss? Did the carbon and water cycles have enough time to fall into rhythm with the changing light source? When these questions enter the picture, the habitable zone is no longer a silent circle around a star. It becomes the relationship between a source of fire and a world trying to preserve its own gentle stability. Perhaps somewhere, a planet orbiting a small star has managed to keep an atmosphere that is thick enough but not too thick, with clouds shading part of the dayside, winds carrying heat into the darkness, and water that was not lost during the star's youth. Perhaps around another sun-like star, a rocky world has preserved oceans, continental rock, and a carbon cycle for billions of years. It is also possible that many planets once had an opportunity and then lost it because the parent star was too violent, because water was broken apart, because the atmosphere was worn away, or because the temperate zone arrived too late after the important ingredients had already disappeared. Each possibility makes the search broader and more humble. We cannot simply measure distance and call a world gentle. We need to read the light, read the sky, read the age of the star, read the faint traces in the atmosphere, and place all of it within a long history. The light source, at the center of a planetary system, does not only reveal the surface, it also reveals the fragility of habitability. A planet needs its parent star to be warm enough that water is not locked forever in ice, but not so powerful that water is pulled away from the surface. It needs enough light for climate to have energy, but not so much radiation that the sky is broken apart. It needs long spans of time, but it also needs the star's youth not to erase the oceans before stability begins. It needs a star that is not perfect, because no star is completely motionless, but durable enough that the planet can learn how to respond. When that happens, light does not only fall onto rock and sea. It becomes the background rhythm for clouds, rain, wind, ice, carbon, and every quiet cycle of exchange that keeps a world with a chance inside the delicate zone between too hot and too cold. In the end, a planet is not habitable only because it has a gentle star, and it does not lose all hope only because its star was once violent. Its fate lies in the way the two meet across time. The star gives energy. The planet retains or releases that energy. The star sends radiation. The atmosphere absorbs it, filters some of it, or is damaged by it. The star changes brightness. Carbon and rain try to regulate heat. The star blows stellar wind. Magnetic field and gravity hold on to part of the sky. Everything is a dialogue lasting billions of years, in which nothing is spoken with sound, but only with light, gas, water, rock, and very slow loss. If distance from the star is the opening sentence, then the temperament of the parent star is the tone that follows the entire story. And in places where that tone is stable enough, gentle enough, and long-lasting enough that the planet is not stripped of what it has preserved, water can continue moving through the sky, carbon can still have a path back, and habitability can have a chance to become a history rather than only a moment in starlight. There are worlds that no longer know sunrise in the way Earth does. On their surfaces, the parent star may hang forever on one side of the sky, never rising, never setting, never sliding across the horizon in the familiar rhythm of day and night. One half of the planet always faces the source of light, receiving continuous warmth like an endless region of daytime. The other half turns away into darkness, where direct starlight never touches the ground. Between those two realms lies a dim transition ring, where light slants low, temperatures may be gentler, winds may blow strongly, clouds may gather, and the climate of the entire world must find a way to connect two halves that seem as if they do not belong to each other. That state often appears in discussions of planets orbiting very close to small stars. Because red dwarfs are dimmer than the sun, the region receiving enough warmth for liquid water lies closer to the star. At such a close distance, tidal forces from the parent star act on the planet over long spans of time, slowing its rotation until one side always faces the star, much as the moon always shows nearly the same face to Earth. From far away, through orbital calculations, a planet like this may still receive a suitable total amount of energy. But on the surface, that energy is not divided evenly by day and night. Light pours down onto one fixed region, while darkness holds another region in deep cold. Habitability then is no longer only about the planet standing at the right distance, but about whether atmosphere, water, and clouds are strong enough to build a bridge between the two halves of the same world. Without a layer of air thick enough, the day side can heat strongly, while the night side continually loses warmth to space. That difference can cause volatile substances to move away from the hot region and condense in the dark region, almost as if the whole sky is being slowly drawn toward the colder side. In extreme cases, the atmosphere can weaken because part of it freezes or becomes trapped on the night side. Water may also be distributed in harsh states, vapor rising in the bright region, ice accumulating in the dark region, while the surface in between endures constant winds, trying to even out the difference. A world like this sounds difficult to keep stable, and the challenge is indeed great. But it is not necessarily hopeless. An atmosphere, if it remains thick enough and flexible enough, can do what bare rock cannot: carry heat far from the place where light falls. Air on the day side warms, expands, rises, and moves toward the darker region. In colder places, it loses heat, sinks, and may return through broad circulation patterns. Winds on a tidally locked planet may not resemble the familiar wind systems of Earth, but the deeper principle is still a temperature difference trying to find a path toward balance. If oceans exist, seawater can take part in that work as well. The sea receives heat in the bright region, currents carry some of that energy toward colder places, and then release it slowly. An atmosphere strong enough and an ocean wide enough can soften a picture that at first seems divided into fire and ice. Clouds can become especially important characters on planets like these. Where the star always stands high in the sky, water vapor rises steadily. Warm air lifts moisture upward, where it can gather into thick clouds around the point receiving the strongest light. If that cloud layer is bright enough, it reflects part of the energy back into space, like a natural curtain shielding the day side from overheating. This changes the initial intuition. A planet that always keeps one side facing its star does not necessarily have a completely dry and scorched day side, because the strong warmth in that region can itself create clouds, and clouds can reflect some light away. But that protection depends on the amount of water, the atmospheric composition, wind speed, temperature, the type of light from the parent star, and the durability of the whole climate system. If there is too much water vapor high in the atmosphere, if the radiation from the parent star is too strong, or if the atmosphere is gradually lost, that cloud curtain may not be enough to keep oceans in place. The eternal twilight ring between the bright side and the dark side often inspires curiosity. That place is not completely submerged in night, and it does not receive continuous overhead light. Starlight may skim low along the horizon, creating a climate region gentler than the hottest point of the day side and less cold than the depths of the night side. If water, atmosphere, and terrain allow it, this transition zone could be a place where temperatures fall into a more comfortable range. But it should not be turned into a simple strip of paradise. Winds may be very strong because air is always moving between the two thermal regions. Clouds may be thick, rain may concentrate, and ice may advance or retreat depending on orbital seasons and atmospheric composition. Everything depends on how the entire planet operates, not only on whether one region lies between light and darkness. A tidally locked world also has no familiar day and night to let the surface rest from light. On Earth, night allows the ground to cool, day warms it again, and that rhythm follows the planet's rotation. On a planet that always turns one face toward its star, the bright region must live with a continuous source of energy that can make water evaporate more strongly, create more persistent clouds, or concentrate climate around one great hot point. The dark region, by contrast, can become a cold storehouse where ice accumulates over long periods. Between the two, the atmosphere has to work without stopping. If it is too thin, the difference may win. If it is thick enough, the planet can weave a network of winds around itself, carrying warmth, moisture, and storms across the boundary between the two realms. The type of parent star makes everything even more complicated. Light from a red dwarf is richer in red and infrared wavelengths than sunlight from the sun, with a different kind of light, a different rotational rhythm, and a different distribution of energy. The greatest challenge is still keeping atmosphere and water over long spans of time. Many small stars can be highly active, especially when they are young, with flares and high-energy radiation. A planet close to its parent star may receive enough warmth for liquid water, but also endure stellar winds and ultraviolet radiation capable of altering the upper atmosphere. If water vapor is carried high and then broken apart, hydrogen can escape into space, causing the planet to gradually lose water. If the layer of gas is eroded faster than it can be replenished from the interior, the surface loses the blanket it needs. In that case, tidal locking is only part of the problem. The deeper question is whether that sky is durable enough to survive the violent youth of the parent star. Even so, these very planets are deeply worth attention, because they show that habitability is not limited to a complete copy of Earth. A world with an eternal day side, an eternal night side, strong winds between the two regions, thick clouds near the point of strongest light, ice in the dark regions, and perhaps oceans distributed in very different ways may still possess zones of stability beyond first intuition. It would not have familiar sunrises, would not have a sky rotating through a 24-hour rhythm, and would not have seasons like the blue planet. But if water remains, if the atmosphere can still transport heat, and if the parent star does not strip the layer of air away too early, gentle stability may appear in another form. The universe does not require every planet to live by Earth's rhythm. This also makes observation both promising and difficult. Planets close to small stars create stronger signals when they pass in front of their parent stars, so telescopes have more opportunities to read light passing through their atmospheres. But the parent star itself can also create noise, with star spots, flares, and changes in brightness that make atmospheric signals harder to separate. A sign of water vapor, methane, or carbon dioxide, if it appears, needs to be placed in the context of the parent star, temperature, orbit, tidal locking, and the history of atmospheric loss. A planet with thick clouds on the day side may hide deeper layers. A planet without a clear signal is not necessarily bare. The signal may be too weak, blocked by clouds, or limited by observational ability. These worlds often give humans only a few outlines in the light, while their true skies remain behind many layers of inference. In the most careful imagination, a tidally locked planet is not a simple sphere divided into hot and cold halves. It may have a large bright cloud region beneath the fixed star, winds blowing from the day side to the night side, ice accumulating in dark regions, oceans moving slowly around continents, rain concentrated in certain areas, and water vapor cycling along paths unlike Earth's. On its climate map, the most important place may not be the point receiving the strongest light, nor the deepest dark region, but the places where exchange is durable enough for water not to vanish, heat not to become extreme, and chemistry to have time to repeat. Habitability, there would be a compromise between fixed light and the constant movement of air, water, clouds, and rock. If Earth teaches that day and night, seasons, oceans, and continents can work together to keep liquid water, then tidally locked worlds teach a different lesson. Stability can find a path under unfamiliar geometries. A planet does not need to rotate like Earth to have a climate worth studying. It needs a way to distribute energy. It needs a layer of air that is not so thin that the dark side freezes everything, and not so thick that it traps heat to an extreme. It needs water flexible enough not to be locked forever on one side. It needs clouds that do not merely cover the planet, but also help regulate light. It needs time long enough for winds and currents to become not just immediate reactions, but stable rhythms of the whole planet. There, the parent star may never leave one position in the sky. Darkness may never leave the opposite side. But between those two realms, if the atmosphere can still breathe in a planetary sense, if water can still move, if clouds can still reflect and retain heat within a moderate range, that world may still write its own kind of balance. It is not gentle in the way Earth is gentle. It is not familiar, not easy to imagine, and cannot be judged by the feeling of a day with sunrise and sunset. But that very strangeness makes the search broader. The habitable zone does not only contain planets turning beneath familiar cycles of day and night. It may also contain worlds where one face looks forever toward the light source, one face keeps forever to darkness, and habitability, if it exists, lies in the silent negotiation between two halves that never trade places. Worlds that always turn one face toward their parent star do not exist only in models. They have begun to appear in real observations, not as clear images of seas, clouds, or surfaces, but as very small changes in light. Each time a planet passes in front of its star, the star's brightness drops by a tiny amount. If that world has a layer of gas around it, a little of the light will skim through that thin sky before reaching the telescope, carrying the traces of molecules. Humans do not see rain falling there. They do not see ice on the night side, clouds on the day side, or winds connecting the two halves of the planet. There is only light, altered slightly by the presence of a very distant world, and within that light are a few clues, enough to open many possibilities. TRAPPIST, one is one of the star systems that makes those possibilities feel closer. Around a small, cool, dim star, 7 planets close to Earth in size orbit, very near one another, in orbits so short that the whole system feels more like a delicate clock than a miniature copy of the solar system. A few of those planets receive amounts of light that have made them noteworthy in the search for liquid water and atmospheres. But the same thing that makes them intriguing also makes them difficult to predict. Because the parent star is so dim, the planets must orbit very close to receive enough warmth. At that distance, tidal forces may slow their rotation until one side always faces the star, while the other remains in extended darkness. What was once imagined for tidally locked worlds is no longer a distant idea. It becomes a question placed upon each small planet in this system. A world in TRAPPIST-1, if it still has an atmosphere, may need to use that layer of gas to transport heat from the day side to the night side. If it has water, moisture may rise in the strongly illuminated region, gather into clouds, and fall in climate zones very different from Earth's. If the clouds are thick enough, they may reflect some light from the side that always faces the parent star. If the air is too thin, the night side may become a place of deep cold, while the day side endures a continuous energy source. Every condition mentioned before meets here: distance, parent star, atmosphere, water, clouds, surface pressure, and time. No factor stands alone. A small planet in that system may receive the right amount of light, but if its sky was eroded when the parent star was still violently active, even a beautiful region of light is no longer enough to keep water on the ground. The difficulty is that those skies have not yet revealed themselves clearly. For Earth-sized planets, atmospheric signals are very weak, while the parent star has variations of its own. Starspots, flares, noise in the light, and the limits of each observation all make the data something that must be read carefully. When a measurement has not found a definite sign of an atmosphere, that may mean the planet has lost its layer of gas. It may also mean the air is too thin, too difficult to read, hidden by clouds, or that the signal is not yet strong enough to separate from the light of the parent star. Within the silence of the data, many possibilities remain. A planet that does not answer immediately does not necessarily have no story. Sometimes it is simply too small and too far away for that story to be heard clearly with current instruments. TRAPPIST-1 is therefore compelling not as a certain promise, but as a test. If rocky planets around red dwarfs can keep atmospheres through the violent youth of their parent stars, if winds and clouds can soften the difference between dayside and nightside, if water is not lost too early, then the habitable zones around small stars will become far broader in meaning. If, on the other hand, many worlds in systems like this are stripped of their skies before they have a chance to stabilize, then the idea of a just warm enough orbit around red dwarfs will need to be understood with much greater caution. Whichever direction the answer takes, that small star system still teaches humanity something important. An Earth-sized planet is not necessarily another Earth, and an orbit receiving just enough light does not necessarily preserve seas, rain, or sky. K-18b takes the story in another direction. This world is not like the small rocky planets of TRAPPIST-1. It is much larger than Earth, may have a thicker layer of gas, and observations have found traces of methane and carbon dioxide in its atmosphere. Those molecules make the planet especially noteworthy because they suggest a chemical environment richer than that of a bare, rocky sphere. Some interpretations have also raised the possibility that beneath that layer of gas there may be a deep ocean, causing K-18b to be discussed as a candidate for a kind of water world under a hydrogen-rich sky. But that appeal comes with a very clear boundary. Being larger than Earth does not mean being like Earth. Having an atmosphere does not mean having a pleasant surface, and having molecular signs does not mean having life. What is notable about K-18b is not a complete picture, but its incompleteness. Light passing through the atmosphere reveals a few components, but it does not tell us how deep an ocean would be if one exists, what the temperature is beneath the gas layer, or whether a surface truly exists in the familiar sense or is buried under immense pressure. Methane and carbon dioxide can tell us about climate, but they do not reveal their own origins by themselves. Some signals discussed as possible traces related to biological molecules on Earth need even more caution, because the same molecule in a different environment can be produced through different pathways. A large planet around a small star, with an atmosphere unlike Earth's, cannot be read through the familiar feeling of the blue oceans of home. Placed beside TRAPPIST, 1 K2-18b reveals two very different kinds of mystery. On one side are small rocky planets, closer to Earth in size, but with atmospheres that remain difficult to confirm. On the other is a larger world that has revealed a few chemical traces in its layer of air, while the deeper nature below remains difficult to name. In TRAPPIST 1, the central question is whether rocky planets still have skies after billions of years near their parent star. In K2-18b, the question becomes what kind of world the sky we have seen is actually covering. One case lacks clear atmospheric data, the other has atmospheric data, but that data opens many interpretations. Together, they pull human thinking away from the simple idea that being in the habitable zone means being close to Earth. These exoplanets also clarify the limits of language itself. When we say methane detected, imagination can move faster than evidence. When we say possibly an ocean, the image of a blue sea immediately appears. When we say habitable zone, listeners easily imagine a temperate place. But in planetary science, each phrase holds only a narrow part of the truth. Methane is a chemical sign that needs context. An ocean, if it exists, may be deep, dark, under immense pressure, and beneath a layer of gas very different from Earth's sky. The habitable zone only says that the amount of light does not rule out the possibility of liquid water under certain conditions. Everything else still has to pass through atmosphere, temperature, surface pressure, water loss history, parent star activity, and chemical pathways that are not yet fully understood. From very far away, Earth too would be only a small planet sending out a few signs. A civilization many light years away could not see people walking on the ground, could not hear rain falling on forests, could not recognize each ocean with ordinary sight. They might measure Earth's shadow as it passed in front of the sun, search for water vapor, carbon dioxide, oxygen, ozone, methane, and other signs in the light. If they were precise enough, they might realize that Earth's atmosphere contains components difficult to keep in balance without living organisms. But to move from a few signs to a real world with rain, forests, microorganisms, seas, and clouds, they would still need many layers of evidence. Thought of in this way, the signals from K2-18b, or TRAPPIST, one become humbler, but also more precious. They are not the final answer. They are the first outlines of a portrait not yet fully visible. Each time humans observe an exoplanet, they are not only looking at that planet, they are also learning how to look back at the conditions of Earth itself. Without an atmosphere, the signal and the light would be poorer. Without water, moisture would be absent. Without rain and rock, carbon would not pass through the slow cycles that have helped maintain the climate of the blue planet. Without a star stable enough, biological signs might never have had time to appear. Distant worlds make familiar things feel less obvious. They remind us that Earth is not only a planet at the right distance, but a system with many layers, each leaving traces in the light. When a telescope reads the atmosphere of a distant planet, it does not hear the whole story. It hears only a few very small notes. One molecule is like a single note. 2 or 3 molecules form a short phrase. But to know whether that phrase belongs to climate, geology, or life, we need to hear more. Temperature, the thickness of the gas layer, clouds, the parent star, orbit, size, mass, and history. Without context, a note can be misunderstood. Methane can come from biology or from non-biological processes. Carbon dioxide can warm a cold planet or be part of a sky that is too heavy. Water vapor can suggest an ocean, but it can also be a sign that water is being carried high and gradually lost. Light is very honest, but it does not explain itself. For that reason, the value of K2-18b and TRAPPIST, one does not lie in allowing a quick conclusion. They matter because they force every conclusion to slow down. A world with notable molecules still needs more observation. A system with many Earth-sized planets still needs us to know whether the skies are still there. A planet in the region of just enough light still has to pass through the tests of its parent star, atmosphere, water, and time. The beauty of these discoveries does not lie in certainty, but in the way they push the question deeper. From where is it to what has it kept? From how much light does it receive to what sky does that light pass through? From which molecular signs are present to what history do those molecules belong to? Perhaps in the future, some atmospheres around TRAPPIST, one will be read more clearly. Perhaps K2-18b will be understood through a different model, or its current signs will be strengthened by later observations. Perhaps another planet, not yet as famous, will become the place where the first pieces of a more Earth-like sky begin to appear. But even if that happens, the lesson remains the same. No single sign can carry the full weight of the word habitable. A network of evidence is needed. Many looks are needed. Alternative explanations must be ruled out. The planet must be placed into the history of its parent star and of itself. The universe does not hide the answer inside one easy symbol. It spreads the answer into many layers, and each layer appears only when humans are patient enough. Those distant planets, in the end, return the habitable zone to its original humble meaning. It is not a ticket into a world with seas and life. It is the position where the questions become more worth asking. TRAPPIST, one shows that a rocky planet around a small star may have to struggle to keep its sky. K2-18b shows that an atmosphere, rich in signs, does not automatically reveal a familiar surface. One side reminds us of the fragility of atmospheres. The other reminds us of the ambiguity of rich data. Together, they bring us to the same point. To understand a world, we have to pass through many doors. Distance is only the first door. Beyond it are the parent star, atmosphere, surface pressure, water, clouds, carbon, time, and the limits of the very light we are using to listen. In the dimming shadow of a planet crossing its star, no ocean appears immediately. There is no sound of rain, no coastline, no blue sky. There is only a very small change in light, so small that without delicate instruments, it would disappear among the countless disturbances of the universe. But that small change is enough to open a door. It tells us where a world exists. Perhaps that world has lost its sky. Perhaps it holds a thick layer of gas. Perhaps it has water in a form very different from Earth's. Perhaps every present sign will need to be understood again. Whatever the case, each time light carries back a clue, humanity learns again how not to rush. And within that refusal to rush, the question of habitability keeps its value, not as a declaration, but as a long act of listening, where each molecule, each shadow, and each silence can make the picture of distant worlds a little clearer. From a very small shadow passing across the light of a star, humans begin to learn how to recognize the existence of a world. No sound of waves returns from that place. No blue of an ocean appears in the lens. No cloud is close enough for us to see it drifting through an unfamiliar sky. There is only light, dimming a little, and then returning to what it was. There are only a few delicate signs in the spectrum. A few molecules leaving very faint marks as starlight passes through the thin layer of gas around the planet. And yet, from signals so small they are almost impossible to hold, humans have begun to build the largest questions. Does that world have a sky? Does it have water? Does it have enough warmth? Can it keep stability long enough? And somewhere among rock, air, water, and time, has chemistry ever crossed into something deeper? But after everything we have passed through, the most important thing is no longer to find an answer quickly, What matters more is understanding why the answer cannot be quick. A planet in the habitable zone is not like a door already opened into life. It is only like a first door that has not been locked. Behind that door, many things still have to be right enough together. Distance from the star must give water a chance, but the atmosphere must preserve that chance. The layer of gas must be heavy enough that water does not leave the surface too easily, but not so heavy and hot that the planet becomes a world buried under heat. Water must not only be present, it must be able to move among sea, cloud, rain, rock, and ice. Carbon must have pathways into and out of the sky so the climate does not slide endlessly toward one extreme. The parent star must be long-lived enough to give the planet time, but not so violent that it erodes the atmosphere before water can become a cycle. This is where the true meaning of the habitable zone becomes clearer. It is not a promise, it is an invitation. It invites humans to look more deeply into a planet instead of stopping at its orbit. It invites us to ask what sky that light passes through, what surface it falls upon, what state it finds water in, how clouds reflect it, how long oceans retain it, and how rock and carbon answer it through cycles so slow that only geological time can measure them. A planet does not become habitable simply because it is in the right place. It has to preserve a long-lasting harmony among very different things. Light that always arrives from outside, an atmosphere that can always be lost, water that can always rise or freeze, rock that changes only very slowly, and a parent star that ages in its own way. Venus, Earth, and Mars have already told us this within our own neighborhood. 3 rocky planets orbit the same sun, yet one world has been pushed into heavy heat beneath a thick atmosphere. One world has maintained oceans and an active sky, and one world has left ancient traces of water on a cold, dry surface. If we look only at distance, the story is too poor. If we look at atmosphere, pressure, water, and history, those 3 planets become 3 different paths taken by the same original material. Venus reminds us that having an atmosphere is not enough, because the sky can also become a trap. Mars reminds us that once having water is not enough, because water needs a durable sky in order to remain. Earth reminds us that gentle stability is not a simple gift, but the result of many cycles quietly supporting one another across very long spans of time. The deepest lesson is not that Earth is so special that nowhere else can resemble it. The lesson is that Earth helps us understand how delicate a planet must be if it is to keep liquid water on its surface. An ocean is not only water. It is a reservoir of heat, a reservoir of carbon, a source of moisture, and the slow memory of climate. Rain is not only weather, it is the pathway that lets the atmosphere touch rock. A river is not only a landscape, it is a current carrying minerals, carbon, and the history of continents toward the sea. A volcano is not only fire rising from the ground, it is part of a deep breath, returning gases from the planet's interior to the sky. Clouds do not only block sunlight, they both reflect light and hold heat, helping decide how a planet responds to its star. These things are not separate. They are connected through very slow cycles, and it is that connection that gives a world a chance not to be abandoned for too long in extreme heat, extreme cold, or dryness. When we look beyond the solar system, that caution becomes even more necessary. K-18b does not become a living ocean simply because its light carries signs of methane and carbon dioxide. TRAPPIST-1 does not become a system full of other Earths simply because it has many small planets orbiting within a noteworthy region of light. These worlds are valuable not because they give us the final answer, but because they teach humans how to ask better questions. A large planet with a rich atmosphere may hide conditions completely different from Earth's. A small rocky planet around a red dwarf may lie in the right thermal zone but may have lost its sky very early. A molecular signal can be an important clue, but it may also have many different origins. The silence of the data may be a real absence, or it may only be a limit of present instruments. The universe does not answer in clear lines of writing. It answers in light, and light needs to be listened to slowly. Perhaps the most beautiful thing in science lies in that slowness. It does not kill imagination, but keeps imagination from leaving the ground. It allows humans to think about distant oceans, but not to forget that an ocean needs pressure, atmosphere, temperature, and history. It allows us to dream of other skies, but not to forget that a sky can be eroded by radiation from its parent star. It allows us to feel moved by a strange molecule in the light, but not to rush into turning that molecule into evidence of living beings. Life, if it exists somewhere beyond Earth, deserves to be searched for with patience large enough to meet it, because if we answer too quickly, we are not truly listening to the universe. We are only hearing the echo of our own desire. The habitable zone therefore becomes a lesson in just enough. Not just enough in a simple sense, like a number placed between hot and cold, but the just enough of many layers existing together. Enough light for water not to be locked forever in ice. Enough atmosphere for water not to disappear from the surface. Enough heat-trapping gas for the planet not to fall into deep cold, but not so much that the surface is heated to an extreme. Enough water for rain to fall, rivers to flow, and rock to weather, but not necessarily so much that the whole planet is buried beneath a deep ocean separating atmosphere from rock. Enough internal activity for gases and carbon to still have a path back to the sky. Enough time for those cycles to repeat not once, but across millions and billions of years. Habitability, understood with care, is not the state of one correct condition, but the music of many conditions not drifting too far out of tune. That is also why Earth becomes more precious after we look toward other worlds. Not because Earth is at the center of the universe, and not because everywhere else is hopeless, but because on this small planet, so many things have been present together long enough for water to become seas, clouds to become rain, rock to become continents with flowing water, carbon to become a cycle of exchange, and life to have time to move from very small reactions to forests, oceans full of organisms, an oxygen-rich atmosphere, and eyes that can look back up at the sky. Each rainstorm on Earth, when thought of in this way, is no longer ordinary. It is evidence of an atmosphere heavy enough, a temperature suitable enough, a water cycle still working, a star stable enough, and a planetary history that has not been cut short. From the outside, Earth too might be only a small point. If someone in a distant star system looked toward the sun, they might see only a faint planet crossing the light, a sign of water, a sign of carbon dioxide, a little oxygen, a little methane, and a few chemical clues difficult to explain without life. They would not see forests breathing, rivers carrying silt, clouds drifting over oceans, or cities lighting up when night falls. They too would have to be patient like us. They too would have to assemble small pieces into a larger picture. Thought of that way, distant planets do not only make us curious about elsewhere, they help us understand that even our own home, seen from the universe, is a secret that would require a great deal of evidence to recognize. What remains after this journey is not a dry list of conditions, but a different way of seeing fragility. A planet can lose water, a planet can lose its atmosphere. A planet can stand in the right region of light, but have the wrong history. A planet can once have rivers and then become a cold desert. A planet can have a thick sky without having a gentle surface. A planet can have abundant water, but lack the pathways for water to meet rock and atmosphere in the necessary way. Habitability is not a bright line drawn around a star. It is more like a very thin thread pulled across many deep gaps. Each condition is a knot holding the thread. If a few knots break too early, the opportunity may fall away from the surface before life has time to begin its story. But that fragility does not make the universe feel colder. It makes the universe more worth listening to. Because if even a few worlds among billions of planets can hold those conditions long enough, if there are only a few places where water truly remains, where rain truly falls, where rock truly exchanges with the sky, where carbon truly cycles, then habitability is no longer an abstract idea. It becomes a story that may be happening somewhere, in the light of another star, beneath a sky unlike our own. Perhaps that place does not have the familiar blue. Perhaps the parent star hangs forever on one side of the sky. Perhaps the clouds are thicker, the seas deeper, the seasons stranger, the rocks different. But if water, air, light, and time can still find a way to meet, that world is still worth listening to. And that is the gentlest lesson the habitable zone leaves behind. It does not teach humans to believe that life is everywhere with ease. It also does not teach humans to despair because every condition is too difficult. It teaches something more balanced. Habitability is a possibility that must be supported, not something that appears automatically, just because a planet stands in the right place. To understand a world, we have to respect each of its layers. To search for life, we have to pass through water, atmosphere, pressure, clouds, rock, carbon, the parent star, and time. To say that a planet may be temperate, we have to understand how it preserves fragile things before they vanish. And to love Earth more deeply, sometimes we need only realize how difficult a thing this planet has done, keeping a thin sky, a wide ocean, a durable water cycle, and a history long enough for life to continue. Perhaps one day, in the light of a distant star, humans will find a sign that can no longer be easily explained by rock, gas, or chemistry alone. Perhaps another atmosphere will reveal many pieces at once. Water vapor, carbon, gases out of balance, a star calm enough, a planet small enough to have a rocky surface, large enough to keep its sky, and old enough for water, not merely to pass through briefly. If that day comes, the answer will not arrive like thunder. It will arrive through many observations, many checks, many times ruling out other possibilities, until the picture slowly becomes clearer. The greatest discovery may begin very small, as everything in this story has begun. A delicate change in light, a trace of a molecule, a question held long enough not to be answered too soon. Thank you for joining the Sleepy Universe on this journey through a concept that seems very simple at first, but opens into many deeper layers the more closely we look. Among the countless stars burning in the darkness, there may be planets standing where the light is just enough, holding skies durable enough, letting water move through clouds and rock in some rhythm we do not yet know. And right beneath our feet, Earth is still turning, still carrying blue seas that absorb sunlight, still forming clouds from water vapor, still sending rain down onto continents, still letting rivers carry minerals back to the sea, still holding a thin atmosphere that keeps just enough warmth for life to continue. And when we understand that the habitable zone is not only about distance from the sun, the familiar sky above us is no longer something obvious. It becomes the sign of a deep balance, where light, water, rock, air, and time have met for long enough that this planet has not fallen silent.